we will share the file which contains the webinar ID for each participant. So I hope that you always check the chat room during these sessions to make sure that you get the file which contains the webinar ID. So that is, I think, one of the pressing issues. Sorry. And yeah, I think today we already have check the chat room already 100 people. So during this session, continue waiting to make sure that you get the file which contains the webinar ID. Then, we can. So that is, I think, one of the pressing issues. Sorry. If you like to ask some question before, I think today we already have we open the event. Please post it in the chat. The chat room already 100 so during this session. Continue waiting to make sure that you get the file which contains the webinar ID. Then, we can. So that is, I think, one of the pressing issues. Sorry. If you like to ask some question before, I think today we already have we open the event. Please post it in the chat room. Get one session. Continue waiting to make sure that you get the file which contains the webinar ID. So that is, I think, one of the pressing issues. If you like some questions, today we already have. If you like ask some questions, today we already have. Please session. Can you chat through that? Get one file. Get the file. If you like thank you for joining in. From Maros 2, from one of the research institute of the Center of Fisheries Research. Welcome to the event.
Good morning, Martin.
Good morning. And who that might be? Oh, Pataruna Mustafa. Thank you for joining in, Pataruna.
You're welcome.
I should have make you one of the presenters, but because we have a really tight schedule, so maybe next time, yeah?
No worries, Mike.
Okay. So,
Pak Hatim.
yes, go ahead.
Jess is joining from Australia. Yeah.
Okay, so let's see if we can find his name on the participant list who are waiting. Yep, Michael Rice. Yep. So wait a minute. Hello, Jess.
Right there, Hatim.
Oh, good. How are you? How is in Sydney? Is still under like some kind of lockdown over there?
It's more relaxed now. So in New South Wales and in Sydney, we haven't had any community transmission or any cases from that type of transmission for 2 weeks now. So people are more relaxed. We still social distance. people are beginning to go back to work at UNSW, particularly laboratory staff, because they're quite important to keep research momentum going. But I think the problem will be when international travel returns, because that will be when, you know, there's a high risk of people coming in with fresh cases of being infected. But anyway, it's a lot better than it was. I hope it's going to improve for you there in Indonesia.
Well, unfortunately, to say that our cases of COVID-19 is increasing right now. Hopefully, well, I don't know, because I think there is like a more than 20-30% increase of COVID-19 infections. So we hope that this outbreak can pass over soon. So, oh yeah, we also have Professor Michael Rice from Rhode Island University. He has joined with us today. So good morning. Oh, not good morning, but good evening.
Good evening,
Professor.
Rice.
Good evening.
Professor.
Thank you. Nice to be here.
Yeah, welcome. Sorry, it's I think almost in the middle of the night in United States. Yeah.
Yes, it is, but no problem. I took a long nap in the afternoon so I could be with you.
Thank you, Professor Rice.
Yeah. So thank you, Professor Rice. I know that United States right now has the same issue with COVID-19 also as well. Yeah. So and then there is like
very
press over there.
Right. Yes. And each of the different states is handling it differently. So luckily, we're not so bad here in Rhode Island.
Okay, cool. Glad to have you here. So thank you so much for joining in.
Okay, very good.
So
are you are you seeing my video, or I don't?
No, I can't see your video. So
Okay, let me see here. Oh yeah, here we go.
okay.
Okay, yeah.
Now,
Yeah, we can see you now.
Yes. Nice living room, Professor.
lots of tropical plants.
Right.
Right, we have the the one there, citrus fruit, begins with a J.
Jeruk.
Juruk, that's the one. Yeah, that's Juruk right there.
Yes. It's basically what do you call it? Citrus or orange?
Citrus, yeah.
Right.
In the Philippines, it's called calamansi.
Okay. Okay then. Thank you, Professor Rice. Let's see if the other speaker also joining in with us.
Okay.
Valentin. Hi, Valentin. Oh, it's not here yet. So, Professor Rice and Professor Jess, the chairman of the Agency of Marine and Fisheries Research and Human Resource, will join us at probably 9:40 or 9:45. So we will still wait for him. I hope that it is okay with you.
Okay, that's fine with me.
Okay. Okay, so when I look into the
Pak Hatim, I think Professor Sarip, the chairman, is already here with us.
okay.
So welcome, Professor Sarip. Yeah.
Thank you. Most welcome to all of you.
Okay, thank you.
Thank you, Pak Chairman. So we will stick with the plan that we will formally open the event at 9:45. And before that, I would like to introduce, even though I already introduced some of the speakers who are able to join us today. Later on, some other will also join with us because they have one or two presenters have a back-to-back meeting, so they will be joining us shortly. So before we open the event, I would like to introduce briefly 6 of our invited speakers. I would like to start with Professor Michael Rice.
Hello?
Please correct me if I'm wrong. So, Professor Michael Rice, he's a professor at the University of Rhode Island. I thought that Long Island, so we made some small mistakes in the.
That's right. That's right. Yeah.
So one of your students correct me. So you are from Rhode Island. Is a one of the states in the United States. Yep.
That is correct. Yes, that's the smallest one.
Right. So Professor Michael Rice has been involved in many research activities and has published many papers and other publications. And recently, I think you are expanding your research into Indonesia. And hopefully that can also improve our state of aquaculture in Indonesia. So later on, me or Ilham will explain more about you when your session is up.
Okay.
And then the second and third speaker is going to be a pre-recorded presentation. So Patrick White from Aquaplan Niva, Greece, and then Chris Cromwell from Scottish Marine Research Association. They will present a pre-recorded presentation regarding carrying capacity and site selection. So both of them have been working together since a very long time, and then they have been involved in research such as in Cyprus, Greece, Philippines, and also last year they visited Indonesia, where I had the chance to meet with them, and they have shared a lot of ideas on how to develop a sustainable mariculture in Indonesia, especially for a large-scale mariculture. And then the fourth speaker will be Valentin Tebot. He's supposedly to join with us right now, but I think he's still in the queuing list. So he is a PhD candidate from University of Sunshine Coast, Queensland, Australia. And the fifth speaker is Dr. Debashis Mazumder, and he is from ANSTO. ANSTO is similar to Batan, Indonesia. It's a national atomic agency, and it is based in Sydney. And he has been developing protocols, methods on how isotope can be used for many research purposes or activities. And the last one will be my former supervisor, Professor Jesman Samut, Associate Professor Jesman Samut. And you will probably know him. He has been involved in Asia projects, at least 3 in different countries in Southeast Asia. So we will introduce more detail about each speaker later on. So it's already 9:37. I think we already have 151 with almost 30 people are waiting in the waiting room. So, Ilham, do you have something to say?
Yeah, I just would like to let the participants know that this international webinar is taking place under the collaboration between the Polytechnic AUP Jakarta or the Technical University of Fisheries of Jakarta and Fisheries Center of the Ministry of Marine Affairs and Fisheries. So on behalf of the University. I am very glad to have you all guys today, and hopefully, after joining the presentation, will be having more views and perspectives on the understanding the challenges and prospects of mariculture development within the framework of an ecosystem approach to aquaculture. So this is a very interesting topic, guys, ladies and gentlemen, and also we are very happy to have here Professor Sarwijaya as the chairman for the Agency for the Marine Fisheries Research and Human Resources, who will be giving the opening speech of this international webinar today. So yeah, Pak Hatim, I think we keep allowing the participants to join, and hopefully now we have at least already 180 participants appear on the screen, and we are keen on seeing more and more to join. Yeah.
Thank you, Pak Ilham, for let's see. Yeah, we also live streamed this event in Polytechnic AUPI TV account, and hopefully, if you know someone who cannot register to this event, or joining into this event, please let them know that they can watch the YouTube live streaming using the provided link in the flyer and in the social media that we provide. So.
So it's like,
yeah,
we can say that this is like a cross-continental seminar if we look at the background of the speakers here. Some of the speakers are coming from the Europe, from United Kingdom, and from Greece. And Professor Rice is now living in the US, and we will have Professor Jasmine and other speakers from Australia. So it's very good, and Indonesia is hosting all those speakers.
That's right.
Yeah.
So actually, I think we also planned to invite one speaker from Japan, actually, but I think due to his really tight schedule, he could not make it to this event. So, but hopefully next time we will hold the same webinar and then invite more well-known speakers to present their ideas, experience, and expertise. So,
yeah, this is one thing that we never imagined before, to have this kind of event. And I think one of the very good lessons we can take from the COVID-19 pandemic, that at the same time, it facilitates all of us, to link. For example, to talk in like academic atmosphere, virtually online, and it's very nice, because it's with less effort, we can get lots of information, lots of things, lots of collaborations, and I think this can be a trigger for all of us to keep improving our performance and our collaboration in the future with other parties, for sure.
right. So, Mr. Ilham, I would like to introduce one of the participants who are, I think, that will determine the future of our mariculture. So I would like to say welcome to Pak Safri Burhanuddin.
Oh yeah, okay. Welcome, Pak Safri. He's one of the deputy in the Ministry of coordinating Ministry of Maritime and Investment.
Yeah, thank you so much for your welcoming. Thank you so much. I appreciate interesting because the title is interesting. The speaker is so interesting. So I enjoy to follow your webinar this morning.
Thank you, Pak. Thank you, Pak, for joining us.
So, Pak Safri, one of the main reasons actually why me and Ilham and I wanted to have this webinar event is that I think I attended one of your meetings, and then you were discussing about developing Mariculture Indonesia, with special focus on developing large-scale industries of mariculture. I think that triggers us to think more about how to balance that kind of economic development with the environmental concern. So how to balance that so that we will have not only like 10 or not only 5 or 10 years mariculture development, but we would like to see that this mariculture development can sustain itself. So that is what basically we want to have an event that can provide an insight on how to achieve that. So
my colleague, sorry, but Mr. Hatim, I have to interrupt you because now already 9:44. So in 1 minute, we'll be starting the event. Yeah. So,
okay, so I will let you to guide through the opening of this event. So please, Mr. Ilham.
Yep. Thank you, my colleague, Mr. Hatim from the Fisheries Center of the Ministry of Marine Affairs and Fisheries, Indonesia. Almost 200 participants are joining us, and we are gonna, soon start the international webinar. Just for your information, ladies and gentlemen, actually, once we launch this flyer, quickly, it's fully booked, and then if we count, we have already like almost 1,000 people interested in joining this event. But we also provide the YouTube link through the Polytechnic AUP TV. So those who cannot join us in this live international webinar, they can also witness or enjoy the session through the YouTube link provided by Polytechnic AUP or the Jakarta Technical University of Fisheries. Well, I have to formally open our international webinar now. Bismillahirrahmanirrahim. Assalamualaikum warahmatullahi wabarakatuh. Good morning, ladies and gentlemen. Our distinguished officer, Professor Sarif Wijaya, as the chairman of the Agency for Marine and Fisheries Research and Human Resources, our distinguished officer, Mr. Sapri Burhanuddin, Deputy of the Coordinating Ministry of Maritime Affairs and Investment, distinguished speaker, Professor Rice from the US, good evening. Distinguished speaker, Professor Jasmine Samad from Australia, good afternoon. Ladies and gentlemen, first of all, I'd like to thank you all for joining our international webinar today, and we are very happy to have you all. And again, this international webinar is conducted under the collaboration between the Jakarta Technical University of Fisheries, Polytechnic AUP, and Fisheries Center of the Ministry of Marine Affairs and Fisheries, Indonesia. We are now in the beginning of the event, and as you are aware that we'll be having opening session followed by a speaker session. So I think because we are limited by time, I would like to give the first chance to Mr. Professor Sarip Wijaya to formally open the international webinar today. And ladies and gentlemen, today we are going, to explore the challenges and prospect for the Indonesian mariculture through the framework of the ecosystem approach to aquaculture. And I think all of us agree that this is a very interesting topic. As a maritime country, Indonesia has lots of potential in terms of aquaculture, and one of the great challenges we are having now and foresee in the future is, to manage these aquaculture resources for the welfare of Indonesian people. So, Professor Sarip Wijaya, please, time is yours.
Well, thank you, Mr. Chairman of the seminar. Bismillahirrahmanirrahim. Assalamualaikum warahmatullahi wabarakatuh.
Salam.
Selamat pagi, salam sejahtera untuk kita semuanya. Very good morning to all invited speakers and participants. First of all, I would like to welcome you all in this event, an international webinar titled The Challenges and Prospects of Mariculture Development within the framework of an ecosystem approach to aquaculture. I acknowledge that this event is the result of the collaboration between the Center of Fishery Research and the Jakarta Technical University of Fisheries. I am very proud that the two institutions under the Agency of Marine and Fisheries Research and Human Resources had worked together to make this event happen in this difficult time. As you all know, that the current COVID-19 pandemic has limited almost every aspect of daily life, including research activities. However, this event poses proof that we are scientists, scholars, academics, practitioners, and government officials can still be creative in always lighting up research activities and knowledge sharing. I would like to offer my sincere thanks to the invited speakers who are willing to share their information, expertise, knowledge, and experience in mariculture and brackish-water aquaculture research and development. Especially to Professor Michael Rice from the University of Rhode Island, Dr. Patrick White from Ekvavalent Niva, Greece, Dr. Chris Comey from SEMS, Scotland, Mr. Valentin Tipot from the University of Sunshine Coast, Australia, Dr. Debasis Mesember from the Australian Nuclear Science and Technology Organization, Australia, Associate Professor Jess Samut from the University of New South Wales, Sydney, Australia, and we have also the distinguished guest, Dr. Safri Buharnudin, the Deputy Minister, Coordinating Minister of Maritime Affairs, Republic of Indonesia. So on behalf of Minister of Marine Affairs and Fisheries, thank you for your effort and support in making this event come true. I really appreciate about that. Distinguished guests, ladies and gentlemen, the Ministry of Marine Affairs and Fisheries has decided to foster the development of mariculture and brackish-water aquaculture in Indonesia. Indonesia brackish-water aquaculture products have been consistently dominating global markets, along with other market players such as China, Vietnam, and Thailand. However, by looking at the effort of these other dominant players to increase their brackish-water aquaculture production, Indonesia realized that we cannot stay in our perceived comfort zone. We have to increase brackish-water aquaculture production, particularly shrimps, milkfish, and other highly valued brackish-water species in order to maintain or increase our position in the global market. Mariculture, on the other hand, developed relatively slow, especially for highly valued marine species such as lobster, grouper, and other finfish species such as barramundi, pomfret fish, and cobia. The biggest production based on volume of mariculture product from Indonesia is currently dominated by seaweed. So, however, the highest value per unit volume of mariculture products come from farm fish species Such discrepancy means the Indonesia could gain more economic benefit by developing farming industries for the highly valued species. The latest published figure of total seascape suitable for mariculture is estimated at around 12.1 million hectares, from which only 2.7% have been used for mariculture. Based on this data, one could argue that the development of mariculture could be extended in terms of the use of available seascape, intensification of the farming system, as well as developing integrated large mariculture industry in Indonesia. Despite its potential economic benefit, these kinds of development pose some negative impacts. For example, excessive development of large-scale mariculture in area with no clear planning of the site management, as well as carrying capacity, might lead to boom and boost development farming. In shorter period, the industry might substantially increase mariculture production. However, in longer run, excessive nutrition to load the environment, disease outbreaks, conflict of seascape usage will render mariculture to a point where it is not economically profitable and environmentally sustainable. That is where an ecosystem approach aquaculture principles comes in to ensure that mariculture and brackish water have to be carried out not only to gain economic benefits, but also to ensure equity and sustainability of the interlinked socio-economical system. I mentioned both mariculture and brackish water in this speech because in Indonesia, both aquaculture systems tend to exist within the same seascape. Their proximity to each other and interaction could speed up the boom and boost even both systems. I hope the presentation from the invited speaker could provide us some insight on how to responsibly and sustainably develop mariculture and brackish water aquaculture in Indonesia, and promoting ecosystem approach to aquaculture as the objective to boosting the socio-economic benefits and ecological sustainability of mariculture and brackish water aquaculture. And finally, on behalf of the organizing committee, I would like to formally open this event. So hopefully we will learn a lot and share information, knowledge, and experiences from this event to achieve sustainable development of mariculture and brackish water aquaculture in Indonesia and beyond. Thank you for all the distinguished guests, participants, excellencies, for your kind attention. I would like to have promoting the productive and fruitful discussion during the webinar. Thank you very much. Wassalamualaikum warahmatullahi wabarakatuh.
Waalaikumsalam warahmatullahi wabarakatuh. Thank you very much, Professor Sharif, the chairman.
To the chairman.
Okay. Thank you very much, Professor Sharif Wijaya, the chairman of the Agency for Marine Fisheries Research and Human Resources. Your time and availability is highly appreciated. And if you still have time, you may keep joining us. Otherwise, we also understand that if you have to join others meeting. But anyway, thank you very much, ladies and gentlemen. I think we can move to the next session, which is the core session today. First, we are going, to have a lecture session, presentation from Professor Rice, who today will be, sharing all of these data information regarding the prospects and challenges in the aquaculture development within the framework of aquaculture ecosystem approach to aquaculture. So I think before I give the time to Professor Rice, I'd like to briefly inform all of us here that Mr. Rice or Professor Rice is now working for the University of Rhode Island at the Department of Fisheries, Animal and Veterinary Science in the USA. And he's actually very, productive and active in terms of the professional, and publication. Professor Rice also have, if we read the curriculum vitae here, he graduated from the University of San Francisco for his Bachelor of Science, and then he continued to take biological science at the University of California, and then he got his PhD at the comparative physiology at the University of California, USA. Recently, Professor Rice is also involving in quite a range of projects and activities, including as the cooperative extension work group from 1987 until now, and in the past he's also the organizing chairman for the first Rhode Island self-fisheries conferences, and then organizing chairman of the second Rhode Island self-fisheries conferences, and some other activities that I don't have to mention here one by one. So also Professor Rice had quite many publications in, for example, transport of dissolved amino acid by the mussel, also in the effects of intensive fishing import on the population structure of guahawks, and some other publication. So Professor Rice, time is yours now, please.
Okay, thank you. All right, so what I'm going to do is, well, first I want to mention that for the occasion, I am wearing the batik of the research station at Gondor.
Oh, thank you very much. I appreciate it.
Thank you, Professor Rice. Appreciate about that.
Special occasion.
Nice.
Yeah.
Thank you.
Okay, so I will try to share a screen here. Oh, someone needs to enable my share screen.
Okay. Yes, and
okay.
you will have 45 minutes, Professor Rice, in total. So yeah.
Okay. So let's see here. Okay, so let's see here. Okay, so what I want to do is sort of discuss this within the topic of our webinar here, ecosystem approaches, and I want to focus on Indonesia and some promises and pitfalls. So the key thing I want to sort of point out is to bring to things, since this is a topic on the ecosystem approach, what I want to bring to the attention of people is a very important document, is the report of the Brundtland Commission called Our Common Future, published by Oxford University Press, they sort of bring out the key elements of sustainability, environment, social, and economic, and each of these needs to be in balance, and how this gets done with an overall thing is governance, and that's going to be different in other places. So we need to be thinking about these three elements at all times. The other thing that I want to bring to the attention of the webinar participants in this topic is a very, very important book by a colleague of mine, Barry Costa-Pierce, who was on the faculty of my department for a while before he moved on to Maine, ecological aquaculture. And there are a number of fine things in there, and I kind of want to get some highlights of this. So let's see here. So one of the things that he was at the University of Hawaii for a while, and did some work on sort of the ecology of Hawaii prior to the English showing up, Captain Cook showing up to Hawaii. What was it like there? And there is some sort of traditional agriculture and traditional fisheries and aquaculture that is going on there. And in fact, it is being taught within the schools there what some of the traditional agriculture and aquaculture is going on. It's basically used as a tool for education. And this is sort of a reconstructed fish pond that is follows the Hawaiian method. We know a little bit about the sort of the landscape and ecology of Hawaii from this 19th century here, and there's some sort of the mountains and zonations in terms of habitat area, and we even see this from the Google Earth shots of the large island of Hawaii with the two volcanoes, Mauna Loa and Mauna Kea, and occasionally they get covered with snow. And so we basically have sort of very, very warm coastal waters going all the way up to these snow-capped mountains on occasion. Now, what the Hawaiians did over time, they developed an agriculture and aquaculture and fisheries integrated system within the watersheds. So there was essentially a watershed management, sort of in the higher areas of the watershed. There is a forest zone with lots of rainfall at the high altitude areas, and there's fresh water that comes down, and there's an integrated farming zone. And then there's a coastal zone with coconut palms, and fish and agriculture are all sort of integrated in this fashion. And if we basically take a look at the sort of the integrated types of agriculture that is done here, we've got non-irrigated, we've got taro and yams and sweet potatoes and bananas, sort of in the freshwater, higher altitude areas. And as we go down toward the saltwater areas, we have fish traps and catching of marine species. But we also have sort of a brackish water species as well, and freshwater fish ponds as well, all in this integrated fashion. And Dr. Costa-Pierce sort of gives a diagram here of the integration of the capture fisheries and enhanced stock enhancement fisheries and aquaculture as part of this. But what's very, very important, and I think is useful for this webinar, is another one of his pictures where aquaculture systems that we're talking about here are very much integrated with animal agriculture and plant agriculture. They're overlapping on these systems, but there is a series of social ecosystems. It's part of sort of a social environment as well. So this is hearkening back to our discussion of the Brundtland Commission and harken back. So we have this sort of visual that Dr. Costa Pierce has come up with. Now, if we, I took this picture here. This is a traditional Philippine fisheries and aquaculture. This is an estuary. I took this photo back in 1982. And what we have here is a series of fish traps where they catch fish and shrimp in the estuary. Here in the foreground, we have an oyster farm, and we have some seaweed farms over here, and we have some farms for grouper, korapu, or what they call lapu-lapu there. Here is a series of ponds for milkfish, which you would call ikan bandeng. Okay, so we've got a lot of different fish going on here in this estuary. All right, now, in recent years, there has been in the literature the developing of this concept of integrated multi-trophic aquaculture coined by Rittler et al. In 2007. Now, as we could see from the ancient Hawaiians and arguably from the Filipinos, they've been doing this for an awful long time, a lot before 2007, some of this type of things here. Would argue that Asian polyculture is integrated multi-trophic aquaculture. We have polyculture of carps here in Chinese, Indian, and Indonesian freshwater pond systems that are often integrated with terrestrial crops. And then we have this sort of marine system here that is developed organically within Asia. And I would argue that these types of traditional systems are in fact a de facto type of integrated multi-trophic aquaculture. And many of the sort of practitioners in and around Indonesia and many other countries of Southeast Asia have some sort of experience, and there's some local knowledge about this that can be drawn upon. All right, so we have issues now. One issue, of course, is now sort of intensification and monoculture, and this focus on the economic aspect of the sustainability. Here is a newspaper article from January 2013 of thousands of fish floating belly up in Jati Luhur Reservoir in West Java, and this has created a lot of concern about the environmental sustainability of various practices. So this basically poses two major questions: is how much fish production is too much, and who makes the decision on how much is too much? All right. So this breaks down to a number of other questions, such as small scale versus ecosystem impact. So one farm may have a small scale impact only locally, but many farms together may even have ecosystem level impacts, overwhelming ecosystem services. But it not only is bad for the farms that it sells, but bad for everything else and kills the body of water.
Cukup SS katanya.
Yeah, and we've seen this here.
Apa?
Okay. Could somebody I can somebody mute, please? Okay. So what we have here now is McKinsey, Inglis et al. 2002, and McKinsey in a major paper talked about 4 kinds of carrying capacity: physical, production, ecological, and social carrying capacity. So physical is just how many fish cages or so can we just physically pack into an area. Production carrying capacity is a carrying capacity at the farm level. How much can we produce without affecting farm production? Ecological, without carrying capacity, without affecting the local ecology. And this social carrying capacity, again, let's get back to the concept that Dr. Costa Pierce and the Brundtland Commission, is that we have this social element as well, sort of social disruption being caused by too much production. So one approach to this is taking a look at carrying capacity models. Model is a representation, and that may be a very simple model. I'll be discussing a simple model a little bit later. Patrick White, a little bit later in this webinar, is going to be talking about some complex models on this, but I want to sort of bring this to introduce everybody to this. There may be some examples here, sophisticated models such as EcoPath of Narragansett Bay here in Rhode Island, and Patrick will be talking about the Tropomod models. There are some mass balance models for freshwater, which are simpler, and we'll be talking about some of that. And then coastal waters, which we're interested in, these marine and brackish water fish. There may be some hydrographic models that might be used here. But what we need to do is kind of keep in mind that we need to be complex enough to realistically describe the system so that decision makers can use the model to some extent, but be not so complex that regulators refuse to use it. We need to be very practical about this. So these are very much the important things to keep in mind. There's some questions of scale as well. There was models to describe loading from single farms in the 1990s. There are some models to describe ecosystem level impacts in the 2000s, and decision support tools for management of cage aquaculture in the 2000s and 2010s. And this will be presented by Patrick White a little bit later. All right, so let's take a look here at a case study. And this is our case study that came out from the fish kills in 2013. We had a grant with URI and IPB, the Faculty of Fisheries and Marine Sciences, University of Surrey and University of Stirling, where we took a look at a number of freshwater lakes and reservoirs around Indonesia. our case study is in Danau Toba. Here was one of the lakes, and here are some of the sort of key aspects on here. The major fish under culture is ikan mas or carps, and later some culture of tilapia. There's some sort of input for the model here. We're going to be using this 1984 beverage model here for this, and we're going to have a feed conversion, the ratio on the feeds and on the amount of phosphorus in the feed. One of the key aspects that we need to sort of keep in mind is that the Danau Toba is multi-jurisdictional. So there's a number of municipalities and districts in the area. So this complicates matters a bit. So the areas where there is aqua farms, there's this Harangatwal Bay, and we have this rather large aqua farm here in the lake. Okay. Okay. And if we actually take a look at here is this Harangatwal Bay and we can basically see here that we're practically reaching physical carrying capacity for pens in this this bay. It's very, very close, large amounts of cages for tilapia and ikan mas. And up close here is a close-up shot of some of these cages. So what some of our students did is take a look at the food conversion ratio, gather some data for the model, and these are the sort of the input data for the model. Another thing that we looked at is the land use around Lake Toba in terms of mapping, whether it is agriculture, shrubs, urban areas, sort of water areas, and take a look at the effect of nutrient runoff from these various things as well. Because what we want to do is know what is coming from the fish and what is coming from the land itself. So how this worked here in terms of phosphorus input for the whole lake thing, it's basically broken down into wastewater, livestock, land use from these various things, and for the entire watershed, and for the Harangatwal Bay itself, sort of broken out here. So in this particular area here, the bay with all of those fish cages has a very, very high amount of phosphorus going into the lake. So here's the average model here, and if what we want to do here is take a look at the trophic status, if we're sort of desired trophic status on all of these, is decide that let's say that we want to have oligotrophic waters for tourism. We would have let's say 12,000 metric tons of fish that would be permissible in the entire lake. But if we said we not interested in tourism, we want to maximize production, we could go all the way up to 183,000. So this is kind of a part of the tools that might be used for managing the lake. For the Haringau Bay itself, what happens is here, if we want to maintain oligotrophic waters, it's not even attainable because the runoff already from the hotels is affecting things. So the best that one can do is only have mesotrophic waters here. Note that the production in Haringau Bay is 27,000 tons, which is much greater than the carrying capacity, which is only 262 at the maximum 20 there. So we're several orders of magnitude above carrying capacity in that bay. So here's some sort of summary findings on this, is that to maintain low mesotrophic conditions, they should really have overall carrying capacity to 33 to 35,000 metric tons, which is about the entire, a little bit more than the entire production of Haringau Bay. And the current production in that bay greatly exceeds the local carrying capacity. But here's our problem: is that exceeding carrying capacity is still happening here. I took this picture at Danau Sentani in Papua just about a year ago, and these are brand new fish ponds or fish cages here, and we're getting localized fish kills there. And there's not very much aquaculture going on yet. So how do we, sort of prevent some of the sort of buildup and intensification? Well, we need to go back again to sort of this ecological and social ecological approach that we're talking about here. So we need to consider the social ecosystems and perhaps provide incentives for integrated multi-trophic aquaculture systems as one way to get around this. However, there's a problem of uneven market value for individual crops. So if we have a company and they had a choice to spend their capital on growing karapu, maybe some oysters and some seaweeds, well, there's more money in the karapu. Let's put all of our money in the karapu. But the problem is that is probably most that's a fed form of aquaculture, and eventually we might get into the problems that we're having in Danau Toba, but now in the coastal zone. How do we incentivize other forms of aquaculture and bring back some of these sort of traditional multi-species aquaculture systems? So the so there's a concept of social costs that need to be having, and the idea is this: is that there are business activities on public lands or public waters accrue direct benefits to the business. So what happens is that you're growing the fish are being grown, you sell the fish, you get the money for the fish. However, the cost of the pollution or these other, what the economists call externalities, are borne by the public, all right? And there's an entire field of environmental economics that are devoted to the quantification and modeling of these social costs. And this may allow for some sort of offsets. All right, so here's an example of how this works. This is an economic model that plots the price of fish. Here is an economic price curve. Here is the cost curve on the bottom here, the cost curve just to grow the fish. However, what happens was the more we add fish, the more it costs to clean up the water. So we have what is called the external cost or the externality cost. These are the social cost curve on top of this. So there's a number of ways of doing this. If we drop the production back on this a little bit, so that we're basically sort of matching, what happens is that we raise the price of fish a little bit, and that sort of takes care of the social costs if we sort of force this to force this back in terms of production. All right. So how would we go about doing this? All right. So what we need to do is we need some data for these economic models here, and you can kind of read about these here, estimates of the remediation of the extractive forms of aquaculture, seaweed, shellfish, benthic invertebrates, and then calculate what these pollution credits would be provided to these aquaculturists that are sort of cleaning up the environment, sort of the seaweed farmers, the shellfish farmers, and so forth. So here are some possible policy alternatives of capping the number of fish pens and providing relatively high fixed permit fees to cover water quality and environmental enforcement costs. We might provide differential permit fees for fish pens and cages and various forms of extractive aquaculture. So the fees for oyster farming or seaweed farming would be lower, or capping the number of fish pens and fish cages and hold auctions for the fed aquaculture permits with a trading system where the some of the permit fees go to subsidize the production of the seaweeds and the filter feeders. So one of the key problems is basically turning research into implemented public policy. How do we do this? So probably like most scientists in KKP are rarely decision makers about this. Very rarely are they, think. And in different countries and localities, there's different governance structures. And a lot of these decision makers are forced with difficult choices. There's many competing interests, and there's a long-term social and economic benefits. And they're hard to sell, particularly if people are up for re-election on a 2-year, a 3-year, or a 4-year cycle. So there's possible of restructuring. This is one thing, and there's possible restructuring of faculties of fisheries at universities to include human dimensions and promote systems thinking about this. And I lay this out sort of as a challenge to the universities with fisheries and marine science faculties to kind of think about this provide locally appropriate extension program for planners and decision makers. So, for example, here, I've been involved here with some cross-disciplinary team members at Cenderawasih University to develop a new faculty of fisheries and marine sciences. And here's the group. Includes not only fish scientists and engineers and fisheries people that we would frequently see, geneticists, feed specialists, but also there's anthropologists, engineers, economists, adult education faculty with joint appointments from their respective home faculties going on. And the idea on this is to incorporate that social dimension within fisheries. Here's an example of some of the work doing in terms of cross-disciplinary trained members and students from Cenderawasih University engage with marine extension agencies in Holtekamp, one of the villages of Jayapura. So some takeaways on this is that some traditional forms of Asian multi-species aquaculture may be in fact classified as IMTA. So many of the sort of like what have grown organically over the decades is cutting edge. It's coming around again. However, there's economic pressure that has forced intensification, and a good way to deal with this is economic modeling of this, possible capping of number of fish pens and fish cages, and we might explore some means to incorporate human dimensions into fisheries education, expansion of the curriculum to fisheries economics, anthropology, and this is very interesting in Papua, since this is it's an area of sort of great social diversity as well in terms of things. That's, you go one village away and they're completely speaking a different language. It makes things rather interesting in terms of the human dimensions, and greater linkages between research and extension to better reach policymakers, because that's where the rubber hits the road, is really some effort in terms of building up the linkages between research and policymakers through the intermediary extension. I've left a number of references here on the slide set for everybody who is interested. And with that, I thank you. Terima kasih.
Well, such a nice presentation from Professor Rice. Thank you very much. So, yeah, you spent 35 minutes, meaning we have remaining 10 minutes for discussion, right? Okay, ladies and gentlemen, for the first session for discussion, I would like to open 3 questions, please. So please, raise your hand or give me any sign. Anybody who is wanting to ask any question, please. Please, Professor Lasara from Halo University, I guess. Please. Hello, Prof Lasara. Any question? Are you giving me sign to question, please? Because here on my screen, or any question, please? I'm still waiting. Anybody who would like to ask any question to Professor Rice?
Yes, me. I have raised my hand.
Okay, please. Oh yeah, sorry, I couldn't see you. Yeah, Pak Taruna.
Okay,
please.
Pak Ilham. Thank you so much for the time. And my question is, being a strategy and a concept as a concept for the ecosystem approach to aquaculture, it has been there for more than a decade. Please, correct me if I'm wrong. However, from my own, personal literature review, very thoroughly literature review, I found that it is still hard to come across any environmental aquaculture approach to aquaculture, the practical framework. That's my point. Even in Indonesia, the former concept, similar concept like good aquaculture practice is still, unsuccessful. We have to remember that the ecosystem approach to aquaculture, it is not what is done or what has been done, but rather how it is done. That's my old concept for the EAA, by which the stakeholder participation is the base of the strategy itself. So my question is there any example like countries, location, or case study from the speaker experiences that has successfully developed a complete set of practical framework of EAA that is used in the decision-making process as expected in the EAA guidelines? That's just my simple question. Thank you, moderator.
Okay, thank you very much. A very nice question. I think, Professor Rice, you can directly answer the question, please.
Oh, okay. Yes. Okay. That is a very good question, and this is one of the reasons that I wanted to put together in terms of my talk, in terms of building up the sort of educational capacity toward this, and also bringing in the human dimensions, such as the sort of the anthropologists and the extension work, so that we're working directly with the Dinas Perikanan at the provincial levels, and actually the provincial governments as well. I've given to Hatim a set of slides that I wanted to share with the group. Is that several days ago, about 3 or 4 days ago, I gave a seminar webinar that was hosted by the University of Calcutta, and I talked about 40 years of work in the Philippines, the estuary where I took that photo. And during that period of time, there was an intensification of the milkfish production. There was net production of milkfish. And up to the point that there were massive fish kills in the estuary, and they had to go through the process of limiting the number of fish pens and managing the carrying capacity of those fish pens. Now, they were able to successfully do it. The however is, and that's the good news. The bad news is that there was an election, a new mayor came in, and boom, the whole thing went away. And the city government basically ran on higher levels of milkfish, ikan bandeng production, and undid everything. So my advice is that it's an exercise in kind of knowing what is right, and trying as best you can to convince people that thinking on the long term is probably the best thing to do. But that's the toughest thing, is basically election cycles are just a few years long, and it may be undone. But don't lose faith, because sometimes it comes through and people will see, oh, this is a pretty good deal.
Okay, so that's the answer for the question coming from Pak Taruna. So next question has been written in the chat box. I already make a record here from Pak Slamet Budi Praitno asking, you professorized, based on your presentation, what is the best step to maintain water quality and aquaculture sustainability in Toba Lake, please?
Okay. All right. So on this particular situation, this is you have basically some of the recommendations. So what the people of the governmental units of Lake Toba need to make a decision of what they want to protect. Do they want to protect the tourism industry there? And if that's the case, what happens is that the carrying capacity or the target for the amount of fish production in terms of tonnage is given at a fairly low number. If they want to be in the middle, there's some higher levels of production, and there's some recommended levels of production if the focus is strictly fish production, and decide that the tourism is not as important. So it's hard for a scientist to make that decision. It's a decision that's made locally. The first question was basically talking about stakeholder involvement and stakeholder decision making. That's the way to go on these things, certainly the provincial governments are sort of key on this in terms of bringing this together. But that's that was an example of different recommendations based on what the local stakeholders want to protect.
Okay.
Okay.
Yeah, thank you for that answer. Next question coming from Pak Indra Cahyono. To Professor Rice, in Sulawesi now is developing the brackish water tilapia. What would you think about the prospect and opportunities for development of technology and its market? Thank you.
Okay, I'm very familiar with the brackish water tilapia because I have colleagues in the Philippines that are working with that, and they're highly marketable, at least in the Philippines. My understanding is that as fish go, they're reasonably accepted in and around Indonesia. It's probably a growth market as fish go, as far as I can see.
Okay, thank you. Any more question, please? We should have, I think, one more question from the audiences, please.
Pak Ilham.
Yes, please, Pak Suaryanto, please. Yeah.
Okay, thank you so much, Pak Ilham. Professor Rice, the FAO initiated this ecosystem approach to aquaculture in 2007, so mostly one decade. What can we learn from the past decade of the ecosystem approach to aquaculture based on your experience by country, maybe in Indonesia or in the other country? Thank you, Professor.
Thank you, Pat. Please, Professor Rice.
Okay, all right. So there is sort of a number of things. I showed you the photograph of the estuary in the Philippines, where I was working in 1982, and in many respects, that is they were doing essentially IMTA fairly successfully there. And how it worked is that it grew up organically. It wasn't thought of. There were people that were growing groupers, the karapu. There's oyster farmers, and there's a few seaweed farmers, and there's these ponds. And the fish, they didn't were not really reaching carrying capacity up until the time when they were started to have very high numbers of milkfish, the ikan bandeng, in net pens, beginning in the early 1990s. And within 4 years of the introduction of that technology, they introduced that technology in 1991. By 1996, about 5 years later, they had overloaded the entire estuary, and there was massive fish kills on there. So they basically went for hundreds and hundreds and hundreds of years, doing oyster farming and a number of doing some milkfish pond farming and so forth like that without a particular problem. It was only when it started to get heavily intensified in the early 1990s that there was problems. Now, there is a colleague of mine at URI who has been doing some work. Her name is Dr. Colleen Suckling, and what she's done is she has a paper on a meta-analysis of IMTA papers in terms of biomass production, total biomass production, and of the various things, and that meta-analysis basically shows that for the most part, the introduction of the biomass production is higher. There's a synergy on these on more often than not. So there's some statistical proof that it does in fact work. But the key problem is the problem of the value there's much higher value in one, and it's enticing certain producers to get into the components of the multi-trophic aquaculture system that may have less value, because for the most part, people are thinking about the money. So that is the key. That's one of the key stumbling blocks.
Okay, thank you, Professor Rice. Ladies and gentlemen, we do appreciate your interest in asking questions, but however, because of the time limit, we cannot accommodate all of you. We still have, I guess, 2 or 3 remaining questions here. If you don't mind, Professor Rice, we will email you all those questions, and then for those who are asking, don't worry, we'll be sending you back all the answer from Professor Rice. Again, it's a very nice presentation. It's the presentation of Professor Rice has given us actually very nice views and insights in understanding context of the ecological approach to aquaculture in the context of ecological aquaculture. and then he already mentioned and noted challenges we have in the Indonesian aquaculture context. For example, INTA, he mentioned about integrated multi-tropic aquaculture. The transformation from research and extension level to policy making processes, and then I think last but not least the system thinking, which remains the homework for I think most of us here as the academics. So thank you very much, Professor Rice, for your very nice presentation. I think we shall move to the next speaker. So Pak Hatim, I have to hand over the session to you, please. Thank you.
Thank you, Pak Ilham. Thank you, Professor Michael Rice. We all really appreciate your presentation. So we still have 6 or 5 more presenters. And the second and the third presenter are actually a one group of presentations, and their presentation are related to each other. So I will share their presentation, and then you can listen the sounds that is embedded in this presentation. And let me introduce you to the two next speaker, Patrick White. Patrick White is working for Aqua Plan Niva, is a consultant in research and development of mariculture based in Greece, while Patrick Crome is a oceanographer, and also he is also a modeler. Previously, he worked for the Scottish Association for Marine Research, and right now he's doing a based on what do you call it? The simplest is he's a freelance, but he has been doing a lot of work in modeling and oceanographic studies. And I think we because right now it's already 10:55, so we better listen to both speakers' presentation. I would like to remind you that because this is an embedded video, presentation, so some of the slide has some problems with voice. Hopefully it does not discourage you to finish watching the presentations. And it will be interesting. I'm sure I make sure that this is a really interesting material. So please enjoy. Oops.
Good morning. I'm sorry I cannot be with you today, but the timing is not suitable for Europe. But I'm recording this presentation so that I can present it to you by myself. I'm going to talk about responsible and sustainable marine cage aquaculture development planning and looking at potential in Indonesia. And I'm using Turkey as a case study for this as an illustration of.
Is everything all right? You can hear the sound, right? Okay, sorry.
Okay. So the talk.
It's okay.
Types of technology, large-scale cage technology. It will look at identifying suitable zones for these technologies, about allocating those zones for aquaculture. It will look at 2 different models which can estimate carrying capacity. and a little bit about licensing and permitting, and then a conclusion. The typical cage technology present used is floating. So these are large, high-density polyethylene pipes made into floating cages with different types of netting, nylon for smaller mesh, and typically Dyneema, a very strong netting for larger sizes of fish, and a frame mooring system, which has anchors or concrete blocks to secure the cages to the location. The other technology is submersible. These are cages which can be submerged under the surface, the water surface, and typically they are used for areas which are more exposed or areas which are prone to typhoons and storms. Also, they are useful if the area has algal bloom, because they can be submerged below the algal bloom, which is typically on the surface. They are useful for reducing problems with sea lice. Again, sea lice tend to be close to the surface. So by submerging the cage during production, they are below the risk area for sea lice. Also, it can be a security measure, sinking the cages when the site is not manned or at night. Looking for potential areas for aquaculture development, typically you use GIS together with suitability criteria. So these criteria are agreed at the start as to key criteria for good aquaculture productivity. And the first one is bathymetry. So that will identify which technology you can use. Current velocity, so the speed, water speed through the cages will, if it's too strong, it's problematic. If it's not strong enough, it can be problematic as well. Waves, so again, it will show what type of technology can be used. The submersible cages, if it's very extreme, prone to large waves. Distance from shore, so it's not too far away to be able to manage and for daily logistics. So using GIS, you can put all these layers together to identify the potential areas suitable for aquaculture. We did a very brief study looking at Southeast Asia, potential areas for the two different types of technology. So for floating cages with bathymetry between 50 meters and 30 meters and 50 meters, and for submergible cages from 50 meters to 90 meters. And we found in Indonesia that for surface cages, there is potential area of 21,000 square kilometers. And for submersible cages, there's 55,000 square kilometers. These are the areas marked in red for submerged cages and yellow for floating cages. So you can look at the potential marine resource for aquaculture development. You can then zoom into particular areas which have more potential area for aquaculture development. So North Sumatra, South Sumatra, Java, Sulawesi. You can also see that some of these areas are quite far offshore on small islands, close to small islands. These may not be priority areas due to logistics, markets, distance to markets, but there may be some others which are closer to airports, ports, and larger towns. We looking at physical carrying capacity. So how many cages can you fit into these potential areas? And we took as the basis an aquaculture zone with 4 large-scale cage sites and as buffers between zones. And looking at how much production if you exploited 1%, 5%, 10% of these areas. So with floating cages and with 21,000 square kilometers, there could be 160,000 ton production per year if 1% of these areas were exploited. With 5%, 800,000 tons. With 10%, 1.6 million tons of marine fish production from floating cages. You can also do this for the submersible cages, which would give higher figures. So it's a huge potential resource for marine fish cage culture in Indonesia. And Indonesia has the largest resource in Southeast Asia for this. Looking at how Turkey underwent the If you look at Lombok, on the left is the potential area for floating cages, in yellow. And then if you add just navigation routes, you can see that some of these yellow areas are in areas which are also used for navigation. So these areas should be avoided in allocation for aquaculture. If you look at all the criteria for identifying zones, you need to look at the essential criteria such as bathymetry, wave height, seabed type, current speed, exposure. Other things that are desirable, distance to shore, distance to a jetty, land facilities on shore. You need to look at potential conflicts, which can be fisheries, tourism, sensitive species such as corals, turtles, and areas which you cannot develop aquaculture in. So military areas, areas close to the border, navigation routes, mooring areas, marine protected areas, etc. At the bottom are the Norwegian classifications for suitability for cages based on wave height and current speed. So in Turkey, they identified 5 potential areas along the Aegean coast. They then undertook the marine spatial planning, allocated those areas, and started issuing licenses. And on the graph on the left, you can see up until 10 years ago, aquaculture was increasing slowly. It was mainly inshore, smaller cage farm systems, but as soon as they started allocating these new areas for aquaculture, then larger companies can come in Mm. But with the large frame mooring, sometimes physical carrying capacity gives you a lower figure than ecological carrying capacity. The second is production carrying capacity. So how much, this is typically used for mollusks and seaweed, so how much food or nutrient is available for production of extractive species. The third is ecological carrying capacity. So how much extra nutrients can the environment assimilate and deal with and still have reasonable water quality and sediment quality in the area. And finally, social carrying capacity. So what will local communities accept in the way of carrying capacity fish production? And this is typically in areas where tourism is important. Again, going back to Turkey, in the top.
Oh, I'm so sorry, because this is our several slides that have a sound problem, so we will move to the next slide.
There are two models that can be used to estimate.
And this one too. I'm sorry.
So basically, you have a volume of water. You have water currents coming in and water currents going out of this volume. You've also got a background level of nutrients coming from domestic, from agriculture runoff, livestock production. If you add aquaculture to this system, you have feed going in, which are nutrients. You have some of those nutrients harvested as fish, but the majority of nutrients are either particular nutrients which are going down to the seabed and accumulating, or dissolved nutrients into the water column. And this model undertakes the mathematical modeling to try and estimate how the water quality in that volume of water based on the level of aquaculture production. And it's quite a complicated mathematical calculation, but it gives you a figure that this volume of water can sustainably produce, say, 1,000 tons. The second model is a depositional model. So this model is looking at the particulate nutrients and traces where they end up. Chris Cromie will give a talk after this talk with more details about this model, but I will just explain some of the outputs and how the outputs are used. So again, it's looking at where nutrients end up, and in this case, it's looking at carbon, so total organic carbon. And it gives you a footprint of carbon under the cages, a predicted footprint. So the brown is significant carbon accumulation under the cages. Green is measurable carbon. White is difficult to measure whether there is a farm there or not. And if there is too much carbon raining down on the seabed, then this is affecting sediment quality, and there will be no animals living in that sediment under the cages. So the output is useful to look at maximum size. So the farms with black predicted heavy or severe impact where no animals, they are too big for the environment. The environment cannot deal with this level of organic nutrients raining down. So they are too big. They should be reduced. It also identifies farms which could be expanded. There is very limited impact. They could be expanded. It also allows distance between farms. So these two different farms are too close together. The brown high impact is overlapping. So one farm is influencing the environment of the other farm. So from this, you can get a maximum farm size and a minimum distance between farms. So you can start to plan how many farms there can be in an area and what is the maximum size that the farms. And then it's a matter of managing those zones, so licensing and permitting. In the case of Turkey, the maximum size of farm was 2,000 tons, and the minimum distance between the farms 500 meters for that location. So then licenses are issued for a specific location and a maximum size of production. And in Turkey and Europe, typically these areas are given 15 to 20 years of the permit to operate the farm on those locations. And they are renewable based on the fact that regular environmental monitoring shows that they haven't impacted the environment badly. So the conclusions from this talk are for planning cage culture is identifying the area and the technology in those areas for the different technologies, undertake marine spatial planning to avoid conflict with tourism, conflict with navigation, environmentally protected areas, to avoid conflict. Then prioritize areas for aquaculture development and for further studies, such as carrying capacity. And you can use these two types of models to look at total production in a zone and maximum farm size and distance between farms. And then a system for licensing, allocating the zone, licensing and permitting. Thank you very much. If you have any questions, please send me an email, pwhite-mobile, one word, @yahoo.com. Thank you very much.
Okay, so that's the presentation from Patrick White. I'm sorry if the sound is a little bit low because his presentation is use a voice embedded in PowerPoint file, so the quality is a bit low. So if any of you will, I will not take any a question and answer in this session because I'm not the presenter, but you will try to record any questions asked by the participant, and then we will forward it to Patrick White. So I think we will move to the next presentation by Chris Cromie. So Chris Cromie will present the depositional modeling using a tropomod, which is a further development of depomod. Depomod is based on a depositional modeling based on temperate fish species. So tropo mode is basically designed to calculate carrying capacity for tropical fish. Hopefully you will also enjoy his presentation. And his presentation will be around 10 minutes.
Good morning, everyone. My name is Chris Cromie, and firstly, I would like to thank Hatim for inviting me to present this morning. And I would like to talk about the Tropomod aquaculture impact model and some of the development and validation work that myself and Patrick White have undertaken in aquaparks in the Philippines. This is an example of a feeding scenario in the Tropomod educational software. The green particles are feed particles and the brown particles are fecal particles, which are slower settling. The top scenario shows good feeding, where there's less feed wasted, and the lower scenario shows a higher amount of feed wastage. You can see on the lower scenario, the seed bed there is coloured red, which indicates a higher level of impact for the poor feeding scenario. This is a schematic diagram of how Tropomod works. We have current velocity of different speed and direction at different depths in the water column, which we obtained from environmental surveys. We have a cage here discharging both fine particles, which are feces, settling very slowly, and we have much larger, faster settling feed particles, which settle generally much closer to the cages. The model produces these contour maps of waste flux. Flux is essentially grams of waste feed and feces per metre squared of seabed per day. And we see this is like a plan view of the seabed, if you like. The small squares are the cages. And you can see 2 rows of cages there, and we have 2 deposition footprints. The different colours represent the different levels of flux and the different levels of impact. So green is moderate impact, orange colours are high impact, and the dark colours underneath the cages represent severe impact. We validated the Tropomod predictions with sediment trap studies. We deployed traps underneath and near the cages for 24-hour periods to collect waste feed and feces. And we compared the observations with Tropomod model predictions of waste feed and feces at those same stations. This shows the Tropomod model validation graph. Essentially, we were able to test offshore milkfish culture at Swal, inshore milkfish culture at Panabo, grouper culture at Panabo, and for a previous project, Filminat project, we had some data for Bolinao inshore milkfish culture. We can see that the red are observations and the green bars are modelled, and we can see that the comparisons of flux are satisfactory for most of these experiments, with the exception of 1 or 2. Further validation of the model, what we did here was we took indicators of impact from grab and core data that was taken around Swal and Panabo aquaparks, and we saw if these indicators of impact correlated with our predictions of waste feed and feces. And we actually found that there was some correlation. Here we have the depth of the black layer in a core, loss on ignition at 2 different temperatures, which is an indicator of organic material in the sample, and percent dry weight, which is an indication of sediment density. We see that we have, where the model predicts high flux, the sediments contained a higher percentage of organic material, and also where the model predicts high flux, the depth of the black anoxic layer in the core was much deeper. So that gives us some confidence that the model can predict these indicators of impact. Criteria for aquapark zoning. Essentially, we kept cages away from restrictions, so this would allow current to flow and enhance flushing through the park. We also had regular spacing between cage groups and between zones to allow flushing through the whole aquapark, and the larger cages, which were offshore milkfish culture, these we had in deeper areas away from the shoreline, and only small milkfish cages or group of cages were permitted to be in shallow areas near to the shoreline. If we just compare that last slide with the current situation at Sewol, here we have a very high density of cages, and there are no distinguishable gaps or corridors between these cages, especially if you look at the way that the current flows, which is from the bottom right-hand corner up to the top of the slide. And you can see that there aren't really any distinguishable corridors through the whole area. Criteria for aquapark zoning in terms of impact. This shows a prediction of flux and benthic impacts for Panabo. And what we did was, within each zone, we tried to maintain a moderate impact, or the green colour, between cage groups. And also between zones, we tried to maintain a moderate impact. In terms of severe impact, we attempted to minimise this underneath the cages, and we did this either by spacing out the cages appropriately or undertaking good feeding scenarios. So this shows the Sewol Aquapark. On the left, the existing situation, and on the right, the reorganised, if you like, revised situation. And we found that when we reorganised the park, we could actually have much less severe impact underneath the cages, and we could also maintain moderate impact between zones as well, and within each zone as well, between cage groups, we could also maintain a moderate impact, which is important for remediation of sediments in between groups of cages within each zone. So we found from our model predictions that regular spacing of the cages and good separation between the zones reduce the impact between culture areas, and we could make some specific recommendations as to distances. For example, inshore zones a minimum of 200 metres separating zones, and offshore zones 400 metres, and also some specific distances within the zones, so 100 metres between cage groups and 25 metres between rows of cages. We also specified a target FCR of around 2 to 1 with careful feeding of a good quality food, which allows a reduction in feed ration. So in this final slide, I just outline how we develop and validate TripleMod for a new area. So essentially we set up the model with cage layouts, bathymetry and hydrographic data. We obtain husbandry data from surveys and input this into the model. We measure any data which is lacking, such as settling velocity of feeds or feces from particular species that haven't been measured previously. We undertake sediment trap validation studies underneath the cages, and we validate the model predictions with monitoring survey data. We then arrive at a validated model which we can use to test management scenarios and assist with determination of carrying capacity. Thank you very much for your attention this morning.
All right, so that marks the end of Patrick White and Chris Cromie presentation. So if I can summarize in a few sentences, so basically what they were talking about is that a good mariculture development should first consider about site suitability, and then after that, the carrying capacity has to be determined. And within that carrying capacity, several factors have to be incorporated in. For example, how far the distance between the zones. And not only that, the distance between the cage should also be carefully planned in order to avoid an overlapping footprint from a nearby cage. So that's what the stickers were talking about. But of course, I would like to remind you all that the positional modeling used by these speakers is just only one of a few or many available tools to determine site selection or carrying capacity. But one of the advantages that their models have been validated in terms of tropical condition, and also have been used in several countries in Southeast Asia. And others, despite their robustness and what do you call it, easy use interface, have been not tested under a tropical condition. But of course, this is an ongoing discussion about how to use the positional modeling. So I think that marks the end of the session for both speakers. I would like to give an applause for them because they will be, I think, watching our video via YouTube next time, because I think in Europe right now is already 7 o'clock or 5 in the morning. Okay, so we will move to the next presenter. I would like to read his CV. Is Valentine here with us already?
Yes, I'm here.
Okay, great. We are glad to have you here. Welcome.
Thank you for having me.
So let me read the short CV or Valentine. Valentine or Valentine? I'm sorry.
Maybe just Val, VAL.
Okay, Val is better. Yeah, cool.
Yeah.
So currently, Val is studying a PhD at the University Sunshine Coast, but he has been he has an experience in research and technical activities. For example, like designing and set up a seaweed production facility for research and development. And also he was involved as a technician in Barramundi hatchery. And his last education before he is undertaking the master degree is a master degree at James Cook University.
That was a bachelor's degree at James Cook.
Bachelor degree. Okay, sorry. So he has some publication, I think, which all the participants could type your name, yeah, in Google Scholar or something like that to find out. So without further ado, Paul?
Yeah, all right, let me just grab that presentation. Thank you, Hatim. Okay, so you're taking care of the screen sharing, of bringing up the presentation?
Okay, can somebody
I have it here, but I'm not allowed to share it, apparently.
I will ask the operators to change you as a co-host.
Yeah, what's your name that appear on the screen here?
It will be V_T. Got it, cool.
Okay, yeah.
All right, 1 second.
Yes, please.
Here it is.
Great.
Can you see it properly, or do I need to go full screen?
Full screen, please.
All right. Okay.
Yeah.
All right. Perfect. Well, thank you, first of all, for having me presenting today. What I'll talk about is on the line of sustainability in aquaculture, looking at fish disease and functional feeds, mainly looking at seaweed. And just because I don't have that much time to talk about everything that I've been doing in my PhD, I'll focus on the rabbit fish, which are quite common in Indonesia as baronang. Most of you guys would know. Just had that slide as a quick background about me. Like Tim mentioned, I was working in a hatchery for Barramundi, worked in a coal power station as a bioremediation technician, so using microalgae to uptake the CO2 and greenhouse gases from the power station. Use microalgae to produce high-value pigments as astaxanthin. And I'm now finishing my PhD, my last semester, last 6 months of PhD, working with a seaweed group at the University of the Sunshine Coast. The reason I'm here and what I'll talk about is one of the main problems in aquaculture, other than all the sustainability issues surrounding the culture of fish, etc., are diseases. Diseases cost the world aquaculture $6 billion every year, so that's a large amount of money. Not only that, the cost of the treatment and whether it's prophylactic or after the disease has reached an outbreak size, is the treatment is costly, time-consuming, can be detrimental to the environment, can be detrimental to us with antimicrobial resistance. The public image of treating fish with antibiotics and other chemotherapeutics are not really good. So getting in front of the challenge, we also have new challenges, including global warming, as most of you would know. Here in Australia, it already did some damage in the salmon industry in Tasmania, where the water reached very high temperatures, too high for the salmon. So what can we do? Functional feeds could be part of a solution. What are they? So the way functional feeds work is that they have to be included in a diet of fish to stimulate the immune system.
Hi, Val. Sorry, can I stop you a bit? I think the screen share is not working, so
okay.
I'm still looking at the first slide of your presentation.
Oh, are you? Okay, that's strange.
I thought that you were opening your presentation, so that is why I let you.
Yeah, I'm on the 5th slide already. Okay, 1 second. Let me share that again and go full screen again. I'll try to.
Can you use the slideshow, or you already did?
Okay, that's what I was doing, but yeah, I'll try to move.
One more. Was it because it's too heavy? Yeah. May I use your PDF file, and then you will ask me to move between slides? Okay.
Yeah, that works. All right, let me stop the sharing.
Okay. Sorry for that glitch, participants. This happens quite often with Zoom system. So give me a sec to pull up Val presentation. So.
it will be better with the slides, hopefully.
Right. So give me a sec. I think I put your presentation in another computer, so.
Okay. Do you want me to try to save it as PDF and I can try to run it like that?
Right.
Okay. All right, let me just open that, see if that works. Okay, let's try again. This time with the PDF, so it's a bit lighter. Here. All right. Can you see that? Okay.
Yeah, clear.
All right. All right. So I'll skip my intro because we've heard that. So these are the photos that was going with it. Disease is a big problem, costing a lot of money worldwide in aquaculture. The treatment of those diseases are also an issue. Costly, time-consuming, not really well seen by the public for some obvious reasons, and can be detrimental for the environment. Oops. So one solution that we have are functional feeds, which are ingredients that basically go into the diet of fish to enhance or boost the immune system of fish, so they are better prepared to deal with stress, bad water quality, and eventually disease and limit actual disease outbreaks. So there's a few different mechanisms how functional ingredients kind of work, either through direct recognition by immune cells of the fish, or through a change in the microbiome towards more beneficial bacteria, allowing an immune response down the track from the fish. What are functional feeds? Here I've got a couple of examples. So beta-glucans are currently used in aquaculture. They are complex sugars from cell wall of different organisms, including fungi, bacteria, yeast, algae, plant, and oats, for example, and that are directly recognized by the immune cells of fish and of ours as well. So it's a good functional feed for us too. Traditional medicine and herbs have been used as well, such as garlic, rosemary, because they do contain some pretty strong bioactive compounds, probiotics, such as lactobacillus strains, and prebiotics, including complex polysaccharides from seaweed, for example, like agar, laminarin, and alginate. Symbiotics are just a combination of both probiotic and prebiotic. Here are some examples of companies that use functional ingredients in aquaculture. So high leases are yeast-based aquaculture supplements here in Australia, in Brisbane, just 1 hour from the Sunshine Coast here. Have a recipe using herbs, and secreting using some as well, which I'm not too sure what the ingredients are. But I wanted to look at a novel ingredient, which are seaweeds, because seaweeds are is a very big group, including more than 10,000 species. They have complex polysaccharides as part of their cell wall, working as structure for those seaweed. Like I said, agar, sodium alginate, and carrageenan. And they can also be rich in strong bioactive compounds, which have a range of different applications, including anti-inflammatory, antioxidant, antimicrobial, anti-tumor, etc., etc. The list goes on and on. I didn't list them all. So during my PhD, the main question was, first of all, what seaweed to use. I mean, there's so many of them. I could only focus on a handful, 11. So I wanted to assess the effect of seaweed in the feed on the innate immune system of fish using Siganus fuscescens. It's a rabbit fish as a model species. And I wanted to also see the effect of the feed on the fish gut microbiome and try to see if there was a correlation between the microbiome response and the innate immune response of the fish, as they may be linked. I had some more slides regarding the mechanism around fish immunity, but I'll make it short and sweet. So basically the immune system for fish or animals usually is divided into two. The innate immune response, which is the first line of response, it's very quick, especially in fish, and the adaptive immune response, which is potent but very slow in cold-blooded species, including fish. So I will only focus on the innate immune response, and from the innate immune response, I will just look at phagocytic activity, lysozyme activity, and alternative complement pathway and respiratory burst activity. Those terms can be a bit fancy for a lot of you, and I had some other slides, but I had to compress it down. I'm more than happy to share those slides that I've taken out, so like that you can have a more better understanding about these. But basically what you can take out from these is that those 4 immune parameters allow the fish to combat disease, and those 4 parameters can be tweaked using functional feeds in aquaculture. And all of them work as a team. It's not just one immune parameter working on its own, it's all of them together. So one of my first micros trial during my PhD was looking at 5 actually, sorry, I forgot to put one here, different species of red seaweed, 3 green seaweeds and 3 brown seaweeds. And I compared that to commercial functional feeds, including hylices that I mentioned earlier, which is a yeast byproduct, and sodium alginate from brown seaweed. I also looked at Hematococcus pluvialis, a microalgae producing strong antioxidant, astaxanthin, and Atrospira patensis, which is spirulina. The way I've done that was pretty straightforward. I collected the seaweed, dried it, and grinded it into a powder, and then added it to a ground. Added water and extruded again into those long spaghettis that you can see here. Once it was dried, I could just crumble it, make some little pieces, some little pellets that I could feed the fish. This is my fish, the rabbit fish Siganus fuscescens. It's present pretty much all around Australia, except in the very southern parts. And it is actually present as well in some parts of Indonesia, I believe, and Japan. So it's widely spread as well. So what I've done is collect blood to look at the innate immunity, and I also dissected the whole gut to look at the gut microbiome. I know there's a lot of other samples in here that I won't be able to talk about, but they're here just for you to have a look at later. So today I will just focus on 2 of those 4 innate immune parameters that I mentioned before, the lysozyme activity and hemolytic activity. And this is me actually drawing blood from one of the juvenile fish that I bred in Australia. It can be very tricky to get blood from. So what did I found after feeding all those different ingredients to the fish after 2 weeks? So that's after 2 weeks on the different diets. We've got the control diet, so unsupplemented diet on the left in the dark gray, and the red, brown, and green seaweed from right to left, the microalgae, and the positive controls in here. So we can see that all the seaweeds, some of the seaweeds actually did improve that lysozyme activity. Basically, the higher the bar is, the more enhanced that activity, that immune parameter is, and the more, supposedly, more resistance that confers to the fish in front of pathogens. as you can see, the microalgae did not do a great deal, and one of the positive control didn't do much either. It was very similar to the unsupplemented diet. Hemolytic activity, same thing, the higher the bar, the better response, the more resistant the fish to diseases. As you can see, there's one clear increase here, which is about 4 times the activity of the unsupplemented control fish. And that's Asparagopsis taxiformis. It's a red seaweed containing a lot of bioactives called bromoforms or brominated compounds, which usually been associated with antibacterial activities and antioxidant activities. Again, some seaweeds do a little bit more than others. Dictyoda here, for example, compared to the other two. Colerpa, that was Colerpa taxifolia, was comparable to the control. And again, the positive control didn't seem to do that much compared to some of the seaweed and even compared to the microalgae that I had in here. Looking at the gut microbiome of the fish. So this is the whole gut dissected from the fish. It's about 3 times the size of the fish. It's a herbivorous fish, so that's why it's so long and so pretty boring. It's basically just a tube that is coiled into the fish. And I section a little piece of the hind gut containing some digesta. I extracted the DNA and had a look at the microbiome, so all the different species, genus of bacteria that are living in that part of the gut. This is, again, all the different treatments that I had before. As you can see, the unsupplemented control diet is sitting in one side of that NMTS. And so it's very unique and different from all the other treatments. There were no real correlation grouping per seaweed category. So the red seaweeds are a bit scattered everywhere. Same with the brown and the greens as well. So it was hard to make sense of it all based on the seaweed that was fed to the fish or different groups of treatments. The top 3 phyla were Proteobacteria, Firmicutes, and Bacteroidetes, which are very common in herbivorous fish. This is another plot looking at the microbiome, just a different, same thing, but different way of looking at it. At the bottom here, we've got the control diet. As you can see, it's quite different from the others. Very low amount of disulfovibrio acid, which are fermenting bacteria, usually associated with digesting seaweed biomass. So that's probably why it was pretty low in that treatment, because I didn't have any seaweed in those pellets. And Archobacter can be a potential pathogen, and it was the highest in the control diet. So we can see that potentially all the different treatments allow the reduction, induce the reduction in Archobacter, which can be detrimental to the fish. So going back to the innate immune response, we can see here is microscopic photos of Asparagopsis. And here are the bioactive compounds that I was talking about before. Asparagopsis was special, as in as a red seaweed. It can store those bioactive in vacuoles, and really it's really concentrated. Just having it with my hands and processing it for a couple of days after, I could still smell the bromoform on my hands. So quite potent plants. So to conclude, the seaweed did have the potential to boost the innate system of fish. Asparagopsis was one of the best performers in this trial. All the different diets led to changes in the microbiome of the fish, but we couldn't find any link between the shift in microbiome and the improvement in innate immunity at this stage. So the other trials that I've done in my PhD, just to give you an idea, because this is not just what I've done, that was back in 2018. I've also looked at the extract of seaweed, just concentrating the power of the seaweed into a very small volume of extract and then adding that into the feed. Also looked at the growth rate of the fish, which was also improved. And I'm now finally looking at the gene expression of immune-related genes in another fish now in Atlantic salmon. And that's me. Thank you very much for listening. Sorry.
Okay, thanks. Yeah, that's great, Val. So I think you only have 10 minutes left for your session for a question and answering.
Okay.
So is there somebody from the participant who would like to ask a direct question to Val? Please.
Me.
Who's me? Can you please introduce yourself?
Sorry, I can't answer for my video. Okay, my name is Waiba. I'm from University of Halu Oleo in Kendari, Southeast Sulawesi, Indonesia. Hi, Val. Yeah, so I'm also graduated from James Cook University for my master degree.
Good job.
Yeah, so I have a question. Since you don't share, you didn't share your feed formulation. I would like to know whether it's similar. The feed formulation is similar to the commercial feed, except for the seaweed ingredients. And is it also the same for microalgae? Are you using the meal, the seaweed meal, and also the microalgae meal? That's my question. Thank you.
Good question. Thank you for picking that one up. Yes, so all the ingredients were dried into a powder, including the microalgae and the different commercial functional feeds came dried into a powder. So all I had to do is, instead of formulating a new fish diet, I use commercially available feed pellets from a manufacturer in Australia. So they came into pellets already. All I had to do was grind those pellets into a powder, so I could blend all the different ingredients within it. So, for example, for ova, one of the green seaweed, I grounded it into a powder and added it to the powdered pelleted feed from the commercial supplier. And that was all the different treatment, all the different ingredients were added at 3% of the weight of that feed. So the composition of the feed was basically whatever I was using from the manufacturer, from that aqua feed. It didn't really change the composition of the feed, just adding 3% of an ingredient. I hope that answered the question.
Yep, okay. Thank you.
No worries.
And so far, you just investigate the effect on the fish immunity, right? Not what about the growth and the survival of the fish?
Yes. So for survival, I didn't have any issue. They all lived. I didn't have any death. And for growth, for that first trial, I used some adult rabbit fish. So for just 2 weeks. So obviously that was a very short time frame, and the fish were really big. So they didn't gain much weight. So there was no significant difference between the unsupplemented fish and the treated fish. That said, in the second trial that I've done after, I looked at juvenile fish. So I bred the adult fish from eggs. I reared them up until they were 2 centimeters. And then they grew from 2 to 12 centimeters in a trial of 4 weeks. So in that one, I did have some significant difference between the seaweed treated fish versus the fish that only had the unsupplemented diet.
Okay, thank you, Val, for the answer. I think we have to let other people to ask questions too. So I have here a question from Linda Rahmi. I would like just read the whole thing. Dear Val, the best formulation can also be administered to a freshwater fish?
Yeah, I don't see any reason why there would be any difference. The amount of response, so I had a very big response for one of my treatments, asparagopsis. So that was 4 times the unsupplemented control. That 4 times may not be the same in another species. So if I tried into another rabbitfish species, even which is closely related, still in salt water, I might still have an improvement, but it's not going to be the same improvement. Regarding freshwater fish, all fish really, all bony-jawed fish have very similar immune system. So there's no reason why it wouldn't work. And I tried it with freshwater fish, salmon, Atlantic salmon, which was both cold water and freshwater, because the rabbit fish I was using was subtropical and saltwater, and it worked as well. So there's no reason why it wouldn't work in another fish species.
Okay. Yeah. I think that also answered the question from Linda. I also got one question again from the University of Palu Oleo. This time comes from Professor Aslan, and I know him that he's really knowledgeable about seaweed, and probably all of us might have read his books or papers about seaweed. Can you please, Pak Aslan, if you want to direct your questions directed to Val, please go ahead. Pak Aslan, Professor Aslan.
Thank you, Pak Hatim.
Yeah, please make it quick, Pak Prof.
Okay, thank you. I just want to know how the Australian government cultivated the asparagopsis. We know that asparagopsis now is presently interested by many seaweed culturists, and in Indonesia also we just try to cultivate the asparagopsis. Hopefully the Australian scientists and Indonesian scientists can collaborate to cultivate asparagopsis, because we know that asparagopsis has high and belong to expensive macroalgae now in the market. Thank you.
Yes, thank you for your question. That's very true. There's a lot of people interested in asparagopsis, not so much for boosting the immune system of fish, but more for reducing methane emission in cows, in cattle, and ruminants in general, and sheep as well. There's different companies, even in Australia, in the United States, in many different countries, New Zealand. We are working with asparagopsis in the lab in smaller, maybe to large scale, maybe 1,000 liter tanks with asparagopsis. But up until now, I don't think there's anyone that can reliably produce it in sufficient amount to both feed the cows and ruminants that we need to in order to curb methane emission and climate change, unfortunately. But any collaboration on that front would be great, I think. And my supervisor working on that is Professor Nicolas Paul at the University of Sunshine Coast, that you may know.
Okay, thank you.
Okay, I think we only have one question from the participant. This is a typical question from a researcher, so I hope that I think you will understand it. So the question is like this: so what are the considerations for you to withdraw the samples on the second week after the treatment, and what the genes that you expect that the treatment will affect? Hopefully can you get that question?
Yeah. So you're talking about the genes for the second part of the question, is that right? Yeah.
Yes.
Yeah. So for the first part, why 2 weeks? Well, the reason why 2 weeks is because in most of the studies, I've done a literature review meta-analysis type, which I've submitted, but it's not yet published. And in most cases, you could see results after a couple of days. So 2 weeks was a comfortable period for us to actually be able to see a change. And also I wanted that time frame to be quite short because I wanted to test as many seaweed as possible. And it was a lot of work to actually work with 16 different treatments. All up, I had 48 different tanks feeding every day, twice a day at the same time. So it was quite intense. For the genes I'm looking at are the lysozyme, salmon, specific to Atlantic salmon, Salmonella, the complement protein C3, the heat shock protein 70, interleukin beta 1, interferon gamma, and that is it for immune-related genes. And I'm also looking at beta-actin and elongation factor 1 as housekeeping genes.
Great. It seems like you remember everything, yeah?
Well, that's very good because I'm doing that in the lab for the past couple.
Right.
Okay.
Yeah. Thank you so much, Val. We still have a few questions on the chat box, but we already run out of time. So if you can help us, you can just chat in the box chat with the participant who will raise some questions.
Sure. And if I didn't answer any questions, I'm more than happy for anyone to contact me by email. I will reply.
Okay. Great. Thank you so much, Val. I think we have to give some applause to Val for his great presentation. Thank you so much.
Thank you, everyone.
Yep. So that's the fourth presenters for today. Thank you so much. And I know it has been a long day, so we have been meeting like for 2 hours straight. But because we have a really tight schedule and the presenters also have like I mentioned at the beginning of this event, they have a back-to-back meetings they have to attend. So we have to continue. We have to soldier on. So Mr. Ilham, do you want to, Mr. Ilham, are you still there?
Yeah, keep going.
Okay, cool. So I would like to invite Dr. Deba Mazumder, if he is already with us. Deba?
Yep. Can you hear me?
Thank you so much. Yeah, I can hear you fine.
All right.
Okay, so before you take the stage, I would like to introduce you to the participant, if that is all right.
Yep, please go ahead.
Okay, so Deba Manzumber is a senior research scientist at the Australian Nuclear Science and Technology Organization, or ANSTO. It has similar function as Batan in Indonesia. And in fact, Batan and ANSTO has, I think, a research cooperation, yeah? Ongoing cooperations. And Dr. Deba has an experience of 25 years in aquatic environmental research. He has published many papers, I think, more than 20. I'm not sure, more than 20, yeah. So, including a publication in Nature. And last year, I think his team, including Dr. Deba, was awarded Australian Museum Eureka Award in 2009 for environmental research. So I think that is all I can tell about Dr. Deba. So I would like to let you present your presentation. Deba, go ahead.
Thank you, Hatim, and thank you, viewers. I guess you are hearing me all right. Is that okay?
Yeah.
Now, it's a good opportunity actually to explain some of the research we have been doing quite a long time. And I have been with ANSTO for last 13 years. And my particular background is environment, ecology, aquaculture, food provenance. So here we are using nuclear tools and technology to modernize the aquaculture, in a sense, to make the aquaculture 21st century up to date. So today, I will give you some example. How do we use our technology and how that technology can bring benefit to the aquaculture industries. So we know that, and previous many of my presenters explained the potential and the possibility of aquaculture and the bottlenecks. Now, as we know that by 2020, the world population will hit 50 billions. So it means we need, there will be intensification or create a lot of pressure to our natural resources to make food available for the human. So I'm talking about all food. Now, because of urbanization, our land size getting shrink every day. And then also, if you see the pollution also is a problem, and intensification of agriculture, although produce a lot of food, but at the same time, intensification of agriculture created a pollution or problem that basically reduce the productive capacity of our land to produce enough food for our human population for the future. Now, what does it mean? So meaning is, either way, we have to look at the ocean resources or water resources to meeting the demand of future food. Now, if we see that, and we all familiar with this kind of graphs, which is published by the Food and Agricultural Organizations, and as we see that the ocean catch, which is the blue dotted line, getting plateaued. At the same time, the aquaculture production increase and the aquaculture demand also increase. So aquaculture now, is one of the fastest growing food production sector in the world. It's already outpaced beef and poultry industry. And if you see some of the literature, they said that, one of the paper particularly mentioned, published in Nature, Ecology and Evolution, and showed that if we carefully managed and carefully organized our ocean farming system, a massive amount of production can be generated, and that will be enough to feed the people in the future. Now, we know this, but at the same time, there are a lot of concerns about the aquaculture expansion, particularly in developed world, like, it's whether it compromise with existing biodiversity, environmental conditions. There are a lot of antibiotics, nutrients, and everything is put in the cases. So how that ultimately affecting in the future growth of the industry is a matter of concern. And we, particularly ANSTO, and they're very closely working in collaboration with UNSW, my collaborator Jesmond Samut, and Professor Jesmond Samut will be talk after me. We have been working for the last 10 years to develop a solution for this kind of problems. So if you say even further, do some literature review, you see there are a lot of concerns raised and there are suggestions. So one of the, among the many problems, we identified two major problems. One is the environmental concern of expansion of aquaculture in general. The other is related to the cost and the nutritional thing. So here they also, have some suggestions which has been discussed in my previous, presenters also touch on these. In generally, encourage farming in the lower food web species, improve feed management and efficiency, develop integrated farming systems, and promote environmentally sound aquaculture practices. And the other one, I'm mostly talking about the food provenance or the certification system. So of these, different issues, here we thought we should focus on the three major areas where our nuclear tools and techniques can play a significant role. One is to minimize the environmental consequences. The other one, how do we use our isotopic and nuclear technology to minimize the cost effectiveness, or make the aquaculture most cost effective, or make the aquaculture having less environmental impact in our farming system, as well as develop a provenance and the certification systems so that we can identify the source and origins of the product. So I will give you some example of our work, and that will show you some of the work we have been doing and we are currently doing with many of our collaborators as well as involving students. Now we are using just an isotopic technique, say for example, and there are a lot of techniques available at this moment, but isotopic technique is one of the nuclear tools which can be used in the development of in minimizing, or say for example, development of feeding strategy, understanding the nutritional requirement and the efficiency of a fish to understand which food, what quantity. So what is isotopes actually? We're talking about, there are a lot of isotopes. So we are talking about stable isotopes, which is non-radioactive. And within that, we are particularly interested about carbon and nitrogen stable isotopes. Why we are using carbon and nitrogen? Because they are the major, carbon and nitrogen are the major building block of any form of life. So here we are talking about, just to give an example, so isotopes are the different forms of the same elements. And say for example, for the carbon, they have carbon-12, which is the lighter isotopes and which is abundant in nature, is around 98%. And then there is a heavier isotope, which we call carbon-13, which is less abundant in the nature. So in the laboratory, we can determine the ratio of carbon-13 to carbon-12, and that gives us some kind of an indication. And how do we trace it? Indication of the food source and its origins and other things. So similarly, we can use the nitrogen isotopes. We can use carbon-14, which is a bit of natural abundant radioisotopes, all these kind of things. Now, it begins with the photosynthesis. So plant use sunlight and produce organic carbon, and subsequently organic carbon is transferred to the food chain through predator-prey relationship, and we can trace the source of origins of the product. So how it works actually in ecological field. So here, say for example, this is a fish. We are all interested about the fish, and suppose this is their food. So if this fish eat this food, the isotopic signal from this food will transfer to this fish upon consumption and assimilation. So similarly, if a fish eat say for example, a red color food, the fish will be red color. If a fish eat yellow color food, it will be yellow color. If a fish eat both red and yellow color food, it will be orange color. So in the nature particularly, they eat many different types of food. So it is a challenge for us to determine which food, what quantity, and that help us to determine our feeding strategy. It is upper hand. It is better than the gut content analysis. Why? Because stomach content analysis, you have to open the stomach of a fish, and it is a bit messy. And this is very difficult to identify what is inside the stomach, because sometimes it will be half digested or full digested. It doesn't give us the full details of the type of food. Maybe the fish just went to the restaurant last night and eat something which is not their main food. So you can end up with, say, okay, this is their food, but actually that is not food. So here the isotopic signal only transfer to a particular species of animal when that is assimilated, and that is the major body of their food. Is it clear? Okay. And then we can use many different kind of calculations of the modeling to understand the changes takes time when a fish eat old food to the new food, and how much it changes from when they eat a food, and then how it changes from the how the isotopic signal from the food changes to the fish when it assimilated. So this is called trophic fractionation factor. and then we can understand how much of the food is used for the metabolism, how much of that food goes for the growth. All these kind of things we can determine based on the need or objectives of your research. So now I can give you some example. We use this technology to oyster aquaculture, tilapia aquaculture, as well as the yellowtail kingfish aquaculture, say for example. Now, first of all, comes to the oyster. You know that oyster is one of the biggest industries globally. I think it is a $1.2 billion industry. In Australia, it is around $50 million industry. Now, successful oyster farming is partly depends on the oyster production in the hatchery. Now, in the hatchery level, they use different algal feed to produce oyster hatchlings or oyster spats, say for example. Now, in the hatchery, they use few different types of algae to develop this oyster spat. Now, here we give an example. How do we use our isotopic technique to determine which algal food is required to the development of a good healthy population of a spat, which can be then transferred to the farmers. Okay, so we use this. So say for example, one of our student, Angela Lu, this is from her honors work which has been published. You can get this paper from there. Here I give an example. How do we use these isotopic signals? So this dotted line is the diet of algae 1, say for example. And again, this dotted line, all this dotted line is basically the algae 1, algae 2, algae 3, and this is the mixed algae. And this line and this is basically a kinetic modeling or a assimilation curve which tells when they start feeding, and this is x-axis is the time. So when they start giving these algae, the isotopic signal of the oyster changes, and some state they start assimilating with the new diet. Okay, this is the simple. Now from this, and this triangle gives us which called trophic discrimination factor, which is a indicator of successful assimilation. All right. Now from these 4 different diets, we can tell diet 3 and mixed diet basically works better. Okay, because the discrimination factor are better and that they assimilated nicely and equilibrated with the food. Now here I just give an example. For this case, say for example, we used our technology for we used this experiment for 15 days. But if our modeling exercise can predict within 70 days, the diet 3 can be fully assimilated and diet 4 will be fully assimilated on 25 days. And through this exercise, we can precisely tell diet 1 or algae 1 and algae 2 is not required of these hatchery level at this stage. Rather, we can select diet 3 or algae 3 or a mixed diet. That way, we can reduce the 2 algae which need to be produced in your hatchery in a commercial scale, and we can easily reduce the cost. Now, this cannot be possible any other means than nuclear technology or isotopic technology. If you do the GUTS content, if you see, you can see that diet 1 or algae 1 also present. But this technology tell you more precisely algae 3 has the better contribution. This actually helping to develop the spat in the hatchery level. And if you see that a small table down here that, you know, the growth and survival rate for diet 3 or algae 3 and mixed diet, the growth performance is better than the algae 1 and algae 2. All right. So now I go to the another example. Here we are doing these, you know, for our, again with the collaboration with UNSW and DPI Fisheries and another of our student, Libby Elizabeth Fabian Levy. She is currently working at the Sydney Water, but she finished her honors work. It was a wonderful work. And here, DPI Fisheries developed few different fast growth performance variety of family line of the oyster. So our objective was to select which family line assimilate nutrient faster and that produce growth. Okay, so here this is another example where we use our nuclear technology or isotopic technology, and we can show you how it works. So say for example, family 53, which is the fastest growing family line, compared to family F09, which is basically a slowest or slow growth family line. So if you see there, this is the yellow line is the diet, and again this is all dots are the isotopic signal of the spat. Once we start giving them the mixed diet, and this triangle again is basically discrimination factor, which is an indicator of dietary assimilation. So family 53, as you see, the discrimination factor for both carbon and nitrogen are smaller compared to family 09, which is the slow growth family. So as you see that means family 53 assimilate the nutrient faster compared to the slow growth family. And if you see that in the diet clearance rate, which is the per cubic algal cell count in the per cubic meter of water, and if you see that family 53, the clearance rate is higher, that means they consume a lot of cells, microalgal cells better or faster than the family 09, which is slow growing things. And similarly, if you see another graph here, if you see the family 53 grow faster than family 09, which is the slow growth. Meaning these isotopic technology can gives you a better understanding how do we use these, and using a small quantity of samples, number of samples, we can easily conclude and assess the assimilation of nutrient, identify the source of origins of the product, something like this. Now we go to another example, which is another of our student, Angela Lu, who is currently end of her PhD, and use determine what kind of feed is needed for yellowtail kingfish, which is finfish, and develop the feeding strategy in this project is again our collaboration with UNSW, Department of Primary Industry, and funded by the FRDC project to DPI Fisheries. Now, just simple an example I can tell you here. Angela used a pelleted food, and also one of the questions we identified, they use choline chloride to enhance the uptake of the pelleted food by the yellowtail kingfish. Now you know that choline chloride is one of the essential nutrient, and that enhance the the nutritional demand of the fish, and without or absence of that, create a fatty liver disease and other slow growing environment and other kind of abnormalities by the fish. So we need a choline chloride, this micronutrient, with a certain amount. The question is how much choline chloride we need actually. So in this situation, we again use isotopic technology. So this graph, people see clearly, this is just a, y-axis is basically the muscle of the yellowtail kingfish and delta 13C value, and this is the different concentration of the choline chloride. So this is another dose response model we develop. Say for example, when we use a very small quantity of choline chloride with the feed, which is basically 0.56 gram per kg of fish, and that time the tissue, and this is the response curve, and we see it is not assimilated nicely compared to this situation when we increase the concentration of the choline chloride goes to 2.5 gram per kilogram of food is better compared to this situation, which is also better. Now, if we compare these three different situations, we see the discrimination factor here is 3.3 parts per thousand. Here discrimination factor is reduced, and it is reduced further. Now, if we add food conversion ratio in these three situations, we see food conversion ratio is much higher when we use a very small quantity of choline chloride compared to 1.15, which is much better, where the discrimination factor is 2.3, and we use 2.5 gram of choline chloride to 1 kilogram of food. Now, comparing this situation, the moral of the study is, you see the discrimination factor is better here, food conversion ratio is better here, and the isotopic assimilation curve is better here. So this situation, we can tell, yes, if we use 2.5 gram of choline chloride to 1 kilogram of food, that combination would work. So compared to that situation where the cost will go high, although there is not much difference between the food conversion ratio between these two situations, but this situation we can stick on, and that gives us an indication how efficiently we can use this kind of technology in many different situations in the aquaculture, nutrition, and aquaculture feeding development. Coming to another example, which is from our another student of Justin Narimbi. He worked with us before, and this is a ACIR funded project and collaboration with UNSW, and Jess will definitely talk a bit of this in his lecture perhaps, and we have been collaborating with him with this project. And here again we use isotopic technology in Papua New Guinea to understand, to compare the objective of the project to enhance the food security and nutritional security for the people of the Papua New Guinea or the farmers of the Papua New Guinea. So they are using food, they are using their current farming practices, particularly some of the farmers use daily feed, some of the farmers use weekly feed. So okay, say which feeding environment is better? What will be the suggestion for the farmers? Whether we can ask them, okay, go ahead with the daily feeding or go ahead with the weekly feeding. So here again, we are using isotopic techniques to understand, okay, let's see what isotope tell us. So here, say for example, we use a feeding in experiment where farmers using daily feeding, and this is the environment where the farmer using weekly feeding. And all these different symbols are the different ingredients of from the pond: feed, algae, sediment, organic matter, phytoplankton, zooplankton, chicken manure, and fish, tilapia. So this black spot is the tilapia, and this orange is basically the chicken manures. And you know that many of our developing country in the farmers using chicken manure. Either they believe that has been directly consumed by the fish, or they also think it may be used as a secondary, and enhance the primary productivity of the pond. But interesting of this work is, we didn't see any of we see maybe very small, we didn't see any major contribution come from the chicken manure in this farming system in both weekly and daily feeding pond. So if chicken manure contribute to the secondary or primary, contribute to the primary, enhance the primary contribution in the pond system, that means all these symbols would be lifted up close to this signal. If fish eat chicken manure directly, then the fish signal, fish and the chicken manure will be close. So we didn't see anything. It was a very surprising result. So one probably possibility is that either the manure they used was fake, was not a good manure, maybe fake manure, we don't know, or other manure has been not used actually, what we have been believed for a long time. So this is actually one of the another breakthrough, we can say. The modern technology and the isotopic technology can refine our farming practices, make the aquaculture more applicable. So further to that, we use some of our technology, again, we use the source mixing calculation, use the isotopic value of the fish and different ingredients, and try to see which pond is better, where, because one is the daily feeding where farmer use daily rationing of food, the other is the weekly rationing of food. So what is the best? And what we see here, where farmer using daily feed, given daily feed to their farms or to the tilapia, so the feed utilization is only 7% compared to the weekly feeding pond, where feed utilization is much higher. I think it is around 33%. So basically what is happening because of farmer, so that means in the daily feeding pond, if you use give the food every day, it is not actually utilized or assimilated by the fish, meaning is you just waste it. You waste your money, you waste your nutritional requirement, you are dumping too much nutrient to the pond. And as you see here, and it also says that detritus material or the algal materials are the major food items for these fish in the farming system. So through this exercise, we can easily determine and identify right food, right amount needed for farming systems, whether it is a pond farming, whether it is a case farming, whether any kind of farming. So this paper also published, and if you are interested of this, you can read and get the details of it. Now, I just touch on, we're almost close to my presentation, so I just touch on other things, which is basically the certification, development of a certification systems or provenance. Now, we know that aquaculture is one of the fastest growing food production sector. However, people, every country, business, consumers are now more concerned. They want to know whether they are buying right aquaculture product, whether they are buying product they are interested to, paying money for this. So as you know that provenance is important and traceability is important, and nowadays 1 in 3 companies in the world are affected by the food fraud, and basically $52 billion loss every year because of the food fraud. And seafood is one of the major industry which is affected by this food fraud or food adulteration. Suppose you go to buy tuna, you end up with something. You want to buy barramundi, you probably buy bacha fillet. So how do we know this? So there are a lot of technology available, which is the most interesting or most applicable or popular technology is DNA markings or gene technology. But here we are talking about some kind of nuclear fingerprint or iso elemental fingerprint, which again ANSTO is collaborating closely with UNSW, and we try to develop this kind of technology over the last few years. And here we are applying this technology we try to develop a fingerprint model and a mathematical model that can give us a very precise and accurate information about the source and origins of the product, where it is coming from, and help us to develop the certification system for the future aquaculture industry. Okay, that will protect the fisheries and aquaculture industry from the fraud or from the other impact. So this range of things we're using isotopic techniques, we're using neutron activation analysis, we are using X-ray fluorescence technologies, and there are a lot of other nuclear tools and technology are using, and then we combine that with our mathematical model. So actually this work is done, one of our PhD student, and is currently half the way of his PhD, and already published 6 papers from his work, from his honors work. So this is just one example. If you're interested, you can read this, and you can contact us as well if you're interested. And currently, we are refining this technology where we are using range of nuclear and isotopic technology, as well as some kind of quality analysis through National Measurement Institute of Australia, which is the part of this project. And this is a consortium of UNSW, Macquarie University, Sydney Fish Market, National Measurement Institute. And all these analytical results will then throw them in a mathematical model, which we developed. And the mathematical model will match the fingerprint coming from these species, and then they predict the source of origin. So our model currently predict over 80% accurately the source and origins of the product, where it is coming from Malaysia, where it is from Indonesia, where it is Australia. If it is Australia, which part of the Australia from? It is a farm product, it is a ocean product, something like that. So we are currently working on this, and we are very much interested, if you guys are interested, to develop collaboration with us in the area of aquaculture, because aquaculture need modern intervention with modern technology to make aquaculture 21st century up to date. So here we have experience, and we are working with many of our partners in the Asia Pacific industry. And Hadim, you probably aware of this when you are here with University UNSW Lab. You often you are very much aware of that work we are doing. So I leave it here for the discussion. You are mute. You are mute, Hatim. You are mute.
Sorry for that. Thank you, Deba. Thank you very much for your really interesting presentation. And actually, we already have a collaboration with the Indonesian Nuclear Institute, and I think our collaboration was supervised by you from Sydney, actually, through the IEA projects. So I would like to let the participant to ask questions. So we have at least 10 or between 5 to 10 minutes of a question and answering session. So please go ahead if somebody wants to raise a hand. Yeah, is there anybody want to raise to ask some questions? Yeah, I know this is because a really new field in Indonesia. For example, Batan. I think one of the researcher from Batan is joining with us. This is a really new thing on how to use isotopic techniques in order to determine the what do you call it? For example, fish feed. What do you call it? The fish feed
requirement, and
requirement, something like that. So, and then, but I think next year we are trying to apply this technique in order to determine how fast the deposition rate of effluent from mariculture, and hopefully that will lead us to do more research related to the technical aspect of mariculture, for example, that you have presented before. So,
Mr. Speaker?
Yes.
Could I ask something for Mr. Deba?
Sure, go ahead.
Yeah, I'm Alexander. Mr. Deba, thank you for your very interesting presentations. I would like to say thank you very much indeed. I know a little bit about, they say about the isotope the table of isotope can can determine how much level of mercury in the fish pond or fish cage, something like that. It means the isotope is like one thing to determine how, to use as an instrument to measure something related to contamination of environment also. So my question is, how come, I would like to link to the food safety issues. How come that if the contamination is radioactive itself, because in the food safety systems, we have two types of contaminants. One from radioactive contaminants and one is non-radioactive contaminants. For non-radioactive contaminant, it's easy for isotope to detect or identify the level of mercury, for example. But for example, chemical. Now, for radio contaminants, so it is possible for isotope detect the source of contamination of the contaminant itself.
Okay, Alexander, thank you for your question. So, look, I think the answer is yes. I explained why. Two things you mentioned. One is the stable isotope and one is the radioisotope. So stable isotopes, the application of stable isotopes are very much in many cases of aquaculture systems or the environmental system you want to measure. This depends on the objective. You mentioned that the mercury biomagnifications of the mercury or the lead to the food chain, so that can be determined by this. Radionuclides or radioisotopes pollution or pollutant can be identified using radioisotopes. And there is a project at ANSTO, and where one of my colleagues, particularly working with the International Atomic Energy Commission agencies to determine the impact of Fukushima, particularly how the radioisotopes and radioactive isotopes are entered to the ocean food web, whether that has a problem for Australia, which is far from the Fukushima, but still are we safe in terms of the food safety? The answer is yes. The radioisotopes can do the job which a stable isotope cannot do. But the problem is the radioisotope analysis can be done in a laboratory condition, because we cannot use radioisotopes in the open environment because it is radioactive. What we are talking here is a stable isotope, which is naturally abundant. And that includes, just give an example, to carbon and nitrogen, but it could be carbon-14, which I also did some work on carbon-14 as well. We can determine the natural abundance of carbon-14 to determine the source of origins of the product. Now, here, if you are interested to do some laboratory experiment to determine, okay, which of the metal enter to a particular chain, we can easily do the radioisotope, we can easily employ the radioisotope, we can do that in the laboratory condition. But we have a lot of other technology, like which I mentioned, X-ray fluorescence technology or a scanning device. We talked about ion beam analysis. We also a little bit I touch the neutron activation analysis. This kind of technology give us a full spectrum of the element present in any food, and that includes give you the ppm value, like your lead, cadmium, arsenic, so whatever. So if we analyze them with our with the neutron activation analysis, you can easily get the how much of the cadmium or how much of the arsenic or how much of the zinc is present. Say for example, any particular type of food. We can do that as well without radioactively, without make the food radioactive. It makes sense?
Makes sense. Yeah. Thank you very much. Very clear. Thank you very much. Appreciate it.
Thank you, Mr. Alexander. Deba, we have another question. The participant is from a research institute in East Java. So his question is like this: considering with the potential use of stable isotopes or nuclear techniques in fisheries, is it friendly or low cost in terms of using it, and is the application is already available in Indonesia, something like that?
Yes. The answer is the scary things come from our psychology and our mind, because we talk about nuclear, oh my God, or something isotopic, oh my God. It is very cheap compared to many other conventional technology. Number one, it requires very small quantity of sample, milligram level to analysis. It requires very small number of analysis from the ecological term or the environmental term. When we have, suppose you go to the fisheries to understand the fisheries food web. So you probably analyze 100 species of fish, and if you analyze 30 of each species, how many fish you have to kill them, okay? But for this, 5 replicate analysis of each fish species is enough with a milligram level of sample. Regarding cost effectiveness, it is very much cost effective, okay, compared to any other conventional, but depends where you analyze. In Indonesia, I think your Bataan having this capacity to some extent, but Bataan and ANSTO are, we have a collaboration, and currently I'm involved in the 2 IAEA funded project where I'm basically the deputy project lead, where Bataan, Ali Arman from the Bataan is involved in this project. Okay, so all these, this project is doing basically develop the capacity of our Asia Pacific neighbor, including Indonesia, in terms of the, capacity of analyzing their samples in their lab. But if we have a project, and that is actually my interest, is to develop a project with Indonesia, and myself, Jess, Hatim, we talked a lot of times. So if we have a project, the Batan and other research institute and Australian organizations, we can work together and we can generate fund. And the analytical cost is really, really cheap. And the technology is not really difficult. It is not that a rocket science. The only thing is we're thinking, oh my God, it is nuclear. And it is quite safe. We are talking about a stable isotope. Meaning is we do not need to do anything. It is there. It is in the nature. It is with you as well. If we analyze your hair, we get some signal, and that signal tells us what you drink, where you drink, whether you drink for the last 1 month is Java water or you drink water from Indonesia in Jakarta water. So your signal is within you. We do not want to contaminate you anything. We just analyze your sample straight away, and that is the stable isotopes.
Thank you, Deba. That's great. Actually, we already passed the time for your session, but we got one question from the person that you just mentioned, Ali Lubis, Ali Arman Lubis from Bataan. His question, I thought that he will ask the question by himself, but instead he sent the question to our group box chat. So here's his question. Sorry, Jess, I think we take a little bit of your time. So I'm from Bataan. I'm Ali Lubis from Bataan. Instead of stable isotopes, are there any other isotopic techniques to quantify the efficiency of food in aquaculture?
Yeah, they do. Actually, there are other isotopes we can use, particularly strontium isotope. We can use also oxygen isotope, but it is all stable. We were embarking about a stable isotope because it is stable. It is non-radioactive, and we can do the job if needed using radioisotope. That is only we can do in the laboratory because we have no permission and nobody has the permission to use this in the open environment. All right. But there are a lot of other isotopes, and there is a massive range of isotopic technique. But here we are talking about a stable carbon and nitrogen because this has been used quite long time, by the agricultural industry, by the fisheries industry. But for the aquaculture sector, it is very much new. And we probably one of the few groups in the world. We means New South Wales University and us. We're probably working for the last few years with this technology, and we developed this technology significantly. And make it applicable to a greater range of aquaculture industry.
Well, thank you, David. I think that is the last question for your session. Thank you so much for joining with us. I really appreciate your effort to make this happen. I think for the participant, I would like you to give some applause to Dr. Deba Mazumder from ANSTO. Thank you so much, Deba.
Thank you.
Okay, now it's already almost 1 o'clock, 10 minutes to 1. So, sorry, Jess, it's been a long day, so but all the presentations are great and I really enjoyed. I hope that also the same with other participants. So I would like you to present your presentation, but before that, I would like to introduce you to the participants. So Jess Monsamut, he's my former supervisor at the University of New South Wales. He has been in charge of several big projects around Southeast Asia, particularly in PNG, Papua New Guinea, Vietnam, Thailand, Indonesia too. And he's a associate professor at the University of New South Wales. He has published many papers with his college, including me too, of course. And then his research expertise ranging from brackish water aquaculture, fish health, GIS application, etc. So he has a very broad knowledge about aquaculture development, especially in Indonesian conditions. So, Jess?
Oh, bugger.
Just go ahead.
Can you hear me and can you see my screen?
I can see your screen, but I think it's a bit, yes, yeah.
There's something in the way. I don't know what that is.
Hi, Jess. I see you, Jess.
Okay. All right. So can you hear me clearly? Because I can't really hear you guys very clearly.
Yes, it's very clear voice from you, Jess.
Okay, fantastic. All right, thanks for the introduction. Selamat siang, everyone, and it's a pleasure to be able to speak to you all. Today I'm going to talk about acid sulfate soils in Indonesia. You know them as tanah sulfat masam. It's an area of research that I've been involved in since about 1993. And I've had the pleasure of working with a lot of Indonesian colleagues, particularly the people from RIKA at Maros. And I've also had the pleasure of supervising about 11 Indonesian postgraduate students, and probably half of them have worked on acid sulfate soils. So my is not... I think I've got the same problem as Val.
Yeah, we cannot really see your screen clearly, yeah.
Yeah, it's not...
I think because it is too heavy, so...
Okay, there we go. Okay, so can you see that? The slide that says acid sulfate soils?
Not yet, yes.
Okay, I can see it on my screen. Should I stop share and start again? I think it worked for Val.
Can you do that?
Okay, let's give that a try.
PDF file to...
Okay, I'm getting a thing that says portion of screen. It's a strange sort of setup. Hang on, I'll do this.
Yep.
Yeah.
Can you see it now?
Ah, yeah.
Cool.
Very clear.
Okay, fantastic. So I'm on the slide that says acid sulfate soils on my screen. Can you see that slide?
Yes.
Okay, fantastic. So what are they? Acid sulfate soils are basically coastal sediments. They do occur in inland areas where there are relict saline soils that have got a marine origin, but by and large we find them on the coast, and they're usually found in areas that are of Holocene age. So they're a product of the last sea level rise, where we've had coastal progradation and accumulation of sediments. And they form as a result of organic matter decomposing and bacteria in that organic matter basically reducing sulfate from seawater in the presence of iron into iron pyrite. And they usually sit there and do absolutely nothing. Occasionally under natural conditions, some layers of acid sulfate soils will oxidise, but generally they're a problem when we excavate them. And the reason why they're a problem for aquaculture, particularly pond-based aquaculture, is that we excavate the soil from below the water table to create the dikes and then convert the area where we've excavated into the earthen pond. As a result of that, oxygen gets into these soils and the pH drops to around 4 or even less. So we tend to call them an actual acid sulfate soil when they become acidic, or a potential acid sulfate soil when they haven't yet oxidised. So very often you'll have an actual acid sulfate soil on top of a potential acid sulfate soil. Now, one of the problems is that the acid that is produced, not only is it directly toxic, but it also mobilises a lot of metals. So things like aluminium, manganese and iron are very easily mobilised. So aluminium will begin to dissolve around pH 5.5, iron around pH 4. Iron is not necessarily chemotoxic in most cases, but it is physically a problem, and I'll explain some of that later on. Aluminium is a problem because it's highly toxic, and surprisingly, as the pH falls, it becomes less toxic. It's more toxic around pH 5.5. And the other sort of pHs you would expect to get in an acid sulfate soil where you've excavated a pond, mainly because tidal action brings in neutralising alkaline waters that tend to maintain the pH above 5 or even around 5.5. So it keeps it under severe conditions in that toxic range. But we do know from other research that even up to around pH 7, once aluminium's been mobilised, it can still exist in a toxic form. So I'm just going to quickly summarise what the key issues are and then talk to a whole series of images, because I think the images will tell a better story than the text will. So firstly, they're going, iron, for example, in acid sulfate soils, when it's mobilised from the soil into the water column, it can reduce primary production. It does it primarily by absorbing phosphate that's available or previously available in the water column. So that can be removed. The other problem is that the acidity on its own can cause oyster mortalities, shrimp mortalities and fish mortalities, particularly if it's a low pH. But the most toxic effect is from the aluminium. So aluminium is going to be the main metal in the acid sulfate soil water, acid sulfate soil affected water, that's going to cause mortality. And I'll show you some slides later on to explain how that happens. It's also a factor in fish disease, particularly because of the damage that it does to fish skin. And it can do that acutely or as a result of chronic exposure. It also affects the growth of fish, and it does it in different ways. Firstly, it can suppress feeding. It can do that in fish, oysters and shrimp. It can reduce the availability of wild feed. It can also stress fish, and that can result in poor assimilation of nutrients. It can also affect the growth of fish by demineralising bones, and it does the same for shrimp. It can affect molting in shrimp. You can get a version of soft-shell shrimp. There's a lot of factors that can lead to soft-shell shrimp or even soft-shell crabs. Acidity is one of those factors. It can clog the gills of fish, oysters and shrimp, and I'll show you some examples later on. And one common factor is where you've got weakly acidic conditions, not enough to kill the shrimp or the oysters or the fish, you can get a lot of variability in the size of the stock, which is not good for the farmer because it then affects the market price. And the other big factor is it does increase pond maintenance costs because there's a higher demand for fertiliser. There's also a higher demand for liming to try to maintain the pH. You also get a lot of cracking depending on the soil type. So here's an example of an acid sulfate soil from northern New South Wales. The grey material that you can see there is about 80% water, which is quite common in Australian acid sulfate soils. The unoxidised layer, which is well beneath the water table, is around pH 7.1. But over here where I've marked it as jarosite, you can see yellow straw-like coloration, and that's one of the indicators that oxidation has taken place. I'm just going to pause there. Can you see this slide?
Yes.
Okay, good. So one issue here is that the jarosite itself, when you lime the soil to try to improve the pH, you can actually release more acidity from the jarosite. It's stable around 3.7 to 4, but as you raise the pH, more acidity is released. And some of the work that we did with Kavita Gasavi, one of my former students, on the acid sulfate soils and shrimp farms in northern New South Wales, were able to show that a lot of the acidity is actually generated by, not by the pyrite itself. So the pyrite oxidation is the trigger. It does drop the pH, but the metals that then dissolve generate more acidity. So you get a lot of mineral acidity. And this mineral acidity is much higher than what we see in acid rain studies in the Northern Hemisphere. It's much higher than the ocean acidification that we often hear about as being a major issue. Now, in Northern New South Wales, where I worked, on average, an acid sulfate soil there, once disturbed, can continue to generate acidity for about 1,000 years, and it can generate about 350 tonnes of sulfuric acid per hectare per year. So once these soils are oxidised, they're a major problem, and it's very hard to go back. You can't, as we say in English, unscramble the egg. So the best thing is to avoid these soils, and I'll talk briefly later on about how we've been doing that over in Indonesia. So mangroves, for example, are a typical environment where we get acid sulfate soils, and many decades ago it was in mangroves where people were developing aquaculture ponds. And ironically, a lot of people are blaming their crop losses to diseases, when in fact, in many cases, it was associated with acid sulfate soils. It just was a poorly understood issue at the time. Give you an example, in northern New South Wales, a lot of our coastal lowlands, particularly in barrier estuaries, have got extensive areas of acid sulfate soils, but sugarcane grows really well on acid sulfate soils. It can grow better on non-acid sulfate soils, but it does quite well on acid sulfate soils. So people see these green fields and don't think there's a problem. So in other environments where you don't have sugarcane, you may see, the encroachment of salt-tolerant species. You'll see the decline of quite a lot of other species that are not tolerant of acidity. So for many decades in Australia, we overlooked the issue, even though it was first recognised in the 1920s. And in fact, a CSIRO scientist in the 1960s raised the issue, but no other soil scientists took much notice. The government didn't take much notice. And it wasn't until we had major fish kills and one person managed to measure the water quality that we realised that we had a significant problem. And then it became an issue. Once it became an issue, we began to address it. This is an example of what has happened throughout Southeast Asia. This is near Makassar. All of these ponds are excavated in acid sulfate soils. Most of these ponds at the time were unproductive. And we launched an ACR project roughly about 20 years ago, where at Maros we established an expert soil assessment team. We established a laboratory to deal with acid sulfate soils and water samples. And later on, we established a mapping team. And all of those teams and the infrastructure that goes with it is still there. Ahmad Mustafa and Tarun Amulia and others that I've noticed here on the list continue to work on acid sulfate soils and ways of remediating them to improve them for aquaculture, but importantly, ways to map them. And Tarun Amulia, for example, did his PhD on mapping acid sulfate soils, did his master's on it as well. And Wirastuti Widyatmanti from Gajah Mada University also did some mapping work. And a lot of that information now is being applied, and particularly led by the Maros group. So if you need to get any information on zoning land and site selection criteria to avoid acid sulfate soils or mapping protocols, it would be the Maros group that you should probably go and talk to. This was in India. I was working in India on fish disease, working with veterinary scientists, and we went out in the field to have a look where the local epidemic was occurring. And my colleagues were saying to me that a lot of these ponds here were not producing shrimp. And in fact, many had been abandoned and there were new ponds being constructed. And I said, well, what was the cause? And everyone said, oh, most likely an unknown disease, a disease that hasn't been described yet. And when I went and had a look more closely at the ponds, I realised that they were in fact excavating into acid sulfate soils. And the pHs, actually at one location, the pH was down to 1.8, which is severely acidic, considering that we look at acidity on a logarithmic scale. So in some cases, it was 10,000 times or even more than that acidic than a normal soil. So in this case, a lot of farms were abandoned. And that's when we basically began to investigate project ideas, and we ended up, rather than working in India, because of bureaucratic issues, we ended up working in Indonesia, and I started working with the late Adi Hanafi. And at the time, Ahmad Mustafa was our understudy. Taruna came along a little bit later on, Rosiana, Hasnawi, quite a lot of people. I won't go through all the names. And we got a lot of momentum on the work in Indonesia because we found that there was well over 100,000 hectares of quite degraded soil environments where farmers were struggling. Some of the indicators of acid sulfate soils are the presence of iron, and usually iron oxidising along the water line, iron suspended in the water. You can also get absolutely clear water, and the reason for that is if there is a lot of aluminium, the aluminium will flocculate suspended particles and they will settle out and give you absolutely clear water. That's dependent again on the level of the pH and also how much aluminium is in that particular soil type. You may or may not get iron in such cases. You get a lot of iron accumulating on infrastructure, and it can also, in some cases, clog pipes if there's significant amounts of it. This is a pond in this is in southern Queensland, and this pond had recurring problems. And one of the issues here was that they couldn't get any primary production. A lot of their post-larvae were dying early, and there was a lot of oxygen stress in the system. So one of the side effects of metals going through their various chemical transformations is that they can also strip out oxygen from the water column. So very often in these sort of systems, they have to aerate the water heavily. So imagine if this was an extensive farming system where you don't have aerators and you have a large supply of oxidizing iron in the system. You can very quickly deplete the oxygen levels. Another indicator in the field, not always present, and it depends on the stage of iron oxidation, is goethite. So goethite is the orange you can see, and the white that you can see on the surface here are basically aluminium sulfate salts, which are very good indicators of acid sulfate soils. But again, you may not see this. You might see iron, or you might see the aluminium, or you might see, for example, lots of this jarosite. So this jarosite is these little yellow straw-coloured streaks that you see in the soil. And as mentioned before, it's problematic because when you lime the soil to improve the pH, you also then release more acidity out of the actual jarosite. This is in Indonesia. I think it was in Parepare, and you can see here some natural oxidation has resulted in hydroxysulfate. That's that white that you see there accumulated in the surface. A biological indicator, very common in the tropics, are nipa palms. So wherever you see nipa palms, you can, with some 90% certainty, know that you've got a potential acid sulfate soil there. So we use that as a biological indicator when we're doing field work, and we encourage farmers to learn a lot about these biological indicators, and the Maros team has invested quite a lot of time and effort into trying to educate farmers about how to understand that you have an acid sulfate soils without having to do expensive soil testing. This is another wonderful biological indicator. Very often we have mud lobster mounds, you will have an acid sulfate soil. And in fact, if you measure the pH at the top of the mound or in the mound itself, where it's oxidised, the pH will be usually less than 4. If you look at freshly excavated material brought up by the mud lobster, the pH might be around 7. It just hasn't oxidised yet. You don't get enough of these mounds to cause a problem, but they are a very good biological indicator. This is in northern New South Wales. Crystal clear water in this canal, but the canal surface is covered in iron. And again, that's an indicator of an acid sulfate soil. The soil pH around this area was around 2. So again, severely acidic. And if you ask most people, where would you go swimming in this photograph? They'd go swimming in that green water. It looks beautiful, okay? And they would avoid the brown water. Well, I would avoid the brown water because there are sharks usually in this river system, in that brown water. But I also would avoid this green water. And the reason why is the pH there is less than 3. And it's less than 3 and has a very high load of aluminium. And the aluminium has flocculated all of the suspended sediment, creating this absolutely beautiful turquoise tropical green water. And for decades, people used to see this green water and think that the water quality was fantastic, not realising that they were fishing and swimming in highly acidic, aluminium-laden waters. And when I did survey work in this system, there was nothing alive. Everything had been killed. So that's basically a very common scenario in estuaries here in Australia, where we have excavated acid sulfate soils for sugarcane and other agricultural practices. And this is a close-up. And in this case, the river water is actually quite fresh after heavy rainfall. The acidic water is fresh, but it is so laden with dissolved metals that it's increased its density and it's sliding in under the main channel water, which is an unusual scenario. It's usually the other way around. So fish kills are one of the most obvious signs when there's a very sudden change in pH. It happens in aquaculture ponds. Usually if the ponds have been dry for some time and then there's been rainfall and a significant acid input has gone into the system. It doesn't happen everywhere, but it does happen. And it can also happen when acid is going through the canal network and people exchange pond waters. So at this particular fish kill, everything was destroyed, except for 2 mullet that I was able to sample for histopathology. So the problem with these sort of fish kills is unless you capture moribund fish, you can't really do any histopathology on them because they decompose very quickly. So the general rule is that you get a moribund fish and you fix it in formalin within about a minute. We used to work off a 30-second rule, actually, and discard anything that we couldn't fix within 30 seconds. People would go to these fish kills in ponds, in estuaries, and they would think that fish were dying from low dissolved oxygen. And they would report that. And I went through a lot of the historical records and fish kills in Australia and found that dissolved oxygen was often the blame. But very often you'd see pHs of around 3 or 4, and people would ignore that. Or they would write in the comment section, the meter was faulty. They used to think the low pH must have been a problematic probe. So they didn't attribute any acidity with the cause of death. They just saw fish gulping on the surface. I went to fish kills, monitored them, and found that dissolved oxygen levels are actually very often quite okay. But the acidity would be around 3. So I would sample fish. So just a very quick lesson. If you follow my arrow, that's the branchial arch. And that arch there has an artery passing through it. And then we've got the gill filaments. So we've got running perpendicular to the branchial arch are the primary lamellae. And then coming off those, I'll show you a scanning micrograph in a second, the secondary lamellae. So healthy gills generally look red. And that's a sign that there is circulation taking place. So these are healthy gills. These are gills from sand whiting, Silago ciliata. And here we have the branchial arch, and coming down along here with the primary lamellae. So we've got an artery, we have a vein, then we've got little capillaries that go through these secondary lamellae. You can see that there are nice little spaces between these lamellae, and the importance of that is that water can pass through. Urea and gas exchange takes place here. So urea is expelled through here, through these secondary lamellae. There's gas exchange taking place, reoxygenation of the blood. So if you've got healthy gills, they look like this. But when you expose fish to acidity, so just a close-up here of the secondary lamellae, you can see the individual epithelial cells. The other thing too is they do play some role in osmoregulation, so there are some chloride pumps in there, but the skin's more important for that. So we want gills to look like this. When they're exposed to acid, they end up looking like this. So all of this material you see here is basically sloughing of the necrotic cells, an accumulation of mucus. You can see the secondary lamellae. If you look at where my arrows are, there's some spaces there. But by and large, at the tips, we have a condition called clubbing, where you get a lot of inflammation, you get a lot of edema, you get a lot of necrosis, you get separation of the epithelium. A lot of blood is trying to pump into the gills to compensate for the toxic insult that's taken place. So they end up looking like this. So a lot of necrosis. There's also mucus cells that have accumulated. And depending on whether a fish is exposed to pH 3 or a pH 5, you will notice some differences. So usually chronic exposure to pHs of around 5 with aluminium will give you this effect. But if you get it down to pH 3, you often don't end up with the clubbing. You just get complete destruction of the actual lamellae. And that obviously affects gas exchange. It affects how they get rid of toxins from their system and so on. The other problem is that acid actually enters the bloodstream via damaged skin and damaged gills. And as a result of that, the blood pH drops. And when the blood pH drops, you end up having a problem where hemoglobin loses its affinity for oxygen. So oxygen transport gets affected. So you've got two problems that contribute to hypoxia in the fish. One is that the gills are damaged, so they've lost their efficiency. And secondly, the bloods become more acidic, so the hemoglobin isn't going to carry oxygen as efficiently as it normally would. The other problem that we have, though, is that as a result of this toxic insult to the fish, the skin, which also plays a role in osmoregulation, is compromised. So you end up getting, in the case of freshwater fish, you might, for example, begin to take salt in saltwater fish. You might get dilution of the blood, so you get salts moving out, depending where they've moved in the system. So just some histosections, and you can see here healthy gills. We've got the primary lamellae. Whoops, sorry, you can see that here. You get primary lamellae. This is damaged now. And the secondary lamellae, we still have some spaces, but we're getting the gill fusion taking place. And again, under severe necrosis and inflammation, we get complete clubbing of the gill. Now, these were gills taken from mullets that's Mugil cephalus, that were taken in a lake in northern New South Wales, in an area where there was aquaculture, but it was eventually abandoned, partly as a result of acid sulfate soil. So this was from chronic exposure to about pH 5 over several days after heavy rainfall. Just checking, can you still see my slides?
Yeah.
Yep, okay, cool.
Good.
All right, so one of the problems in aquaculture that's occurred through Southeast Asia, we had epidemics and pandemics about 20 years ago. It's not as common as it used to be, but still occurs, and it happens in estuaries, here in Australia in particular, and that's outbreaks of epizootic ulcerative syndrome. So many years ago, I worked with veterinary scientists to try to understand what were the causative factors for this. We knew that this disease was caused by Aphanomyces invadens, a fungus. Many studies around the world kept blaming bacteria, viruses, etc., but it was in fact a fungus. We were able to reproduce, apply Koch's postulates and be able to prove this disease occurs as a result of a combination of factors. The factors for us were skin damage. You needed to have skin damage, you needed to have the fungus, and obviously you needed to have a susceptible host, which in this case is the fish. The question was, what was causing the skin damage? Now, this isn't the case for all examples of EUS outbreaks around the world, but in Australia we found that there was an association with acid sulfate soils. These fish disease outbreaks occurred usually 10 to 14 days after fish kills or after the river systems became acidified. So we hypothesised that acidity was causing skin damage. So my PhD, many years ago now, was about looking at, could acid firstly cause skin damage, and working with Dick Callanan, we were looking at whether in the presence of fungal spores could we reproduce this disease, and we were able to do that. So this is these are shots of Selago ciliata showing some gross pathology, what happens when fish are exposed to pH 3.1. These fish obviously didn't survive that pH, but during a moribund state they were collected, and you can see here that there's congestion of the blood vessels. It happens along the dorsum and also the caudal peduncle, and you get this, again, look of pallor, and you also see that in the gills. So this was without any exposure to fungal spores. Here are some lesions, early stage lesions of epizootic ulcerative syndrome in bream that I sampled up in northern New South Wales about 7 to 10 days after a fish kill and after the system became strongly acidified. And these lesions would have progressed had we not collected these fish. To give you an idea, normal skin looks like this. If you follow my arrow where we've got EPC, we've got a pavement layer of epithelium there made up of epithelial cells. So this is your epidermis, and the epidermis is usually about 3 to 4 cells thick. Here we can see some goblet cells. The next layer down is a stratum spongiosum. It's been slightly separated here as a result of sectioning. And we have a scale coming through here. Whoops, you go back. Down here we have the stratum compactum, again separated here because of the sectioning. And down here we've got the connective tissue. So this is the muscle. So healthy skin generally looks like this. We have a non-keratinized epidermis. So unlike humans have a keratinized epidermis. We can scratch our skin and not cause too much hassle. If you grab a fish and you scrape the surface, you expose the fish to infection. So our theory was that the acid was destroying this epidermal layer and then therefore exposing the fish to pathogens. In our case, the pathogen of interest was Aphanomyces invadens, a highly aggressive fungus. This is an example of a fish skin from a fish exposed to acidity, and the epidermis is destroyed. It's gone. And there's some edema and necrosis all through here. That's the scale there. You've got necrotic epidermal cells. Basically, the integrity of the epidermis is gone. So this leaves the fish exposed to any pathogens that might be swimming around in the water. Now, when we put healthy fish into basically a soup of fungal spores, they didn't get any evidence of early stage EUS. And we left them in there for a week and kept replenishing their environment with new spores, and they would not get infected. By contrast, when we put fish in with skin damage that survived, so we used a weak acidic tank experiments. We did some for fish kills. We ran those out until they were actually morbid. But in this case, we used sublethal exposure to get enough skin damage, because some fish survive fish kills. They swim into environments where the Aphanomyces spores occur, usually in fresh water after heavy rain, and the main channel, which is normally brackish, can become fresh. And we got infections. So what we did was look at micrographs from scanning electron microscopy. This is a normal surface of the epidermis. So this is the pavement layer. You can see the micro ridges. These micro ridges increase the surface area of the epidermis. It also creates a rough surface for mucus to attach to. So a normal fish, it looks like this. But when exposed to acid, you get necrosis. So these are necrotic cells, and you can see over here where my arrow is on the left, where you've got some of the epidermal cells still intact, but they would eventually break down as well. So our Aphanomyces spore and lots of other fungal spores and protozoans, etc., swimming around the water column, would come into contact with this skin. So a fungal spore hits the skin and sends this germination tube down. When we did the histopathology on it, we couldn't find fungal spores until we did serial sections. And what we found, it only took 1 or 2 spores to set up an infection. And eventually, the skin creates a new, very fine, thin layer of epidermis to try to repair. So that it's out of the acid water, it's gone into circumneutral water, it's recovering. It creates this very thin layer of epidermis. The spore is entrapped under it, and the spore begins to germinate. It begins to grow hyphae, and the hyphae burst out like you see here. And you can see in this case, there are new spores ready to come out, those little dark sections. And down here at the base, enzymes are being released, which are breaking down the new epidermis. And underneath the skin, right down into the dermal layer, those enzymes are beginning to break the skin down even further. We just can't see it at the moment. And then more and more of these hyphae break through, more enzyme activity. Oops, sorry about that. And then you get a fungal mat that looks like that. And eventually, after about 7 days, you get an ulcer like this. So obviously, if you're a fish farmer or if you're a commercial fisherman, you would not want to be selling this fish. In New South Wales, up to 80% of the wild catch at some point when we were having these outbreaks were infected. And in aquaculture ponds, it was also problematic. The other issue is that with skin damage, a lot of other fungal diseases become a problem. This was some work that we did, and I was routinely going through sections of a particular wetland that were being acidified, and there was a population of gudgeons, the genus is Gobiomorphus, that were exposed to a very slow decline in pH, to the point where they were actually acclimatizing. But then there was a sudden drop, which I think increased the acidity by about 1,000 times overnight. The fish survived, they had some adaptability, but saprolegnia fungus then invaded, and there was a mass mortality as a result of the saprolegnia basically covering all the fish. Under weakly acidic conditions, you can get bone demineralisation that can lead to things like scoliosis and kyphosis, not in the traditional sense that those diseases occur in humans, but in fish it's a demineralisation process. So the fish might be living at around pH 5.5 to 6. The aluminium concentrations may not be high enough to cause any lethal outcomes, but high enough to help displace calcium and other minerals from the bone structure, and the blood pH drops a little bit too. So they become less effective at respiration. So this is another common factor. Stunted growth is very common as well. In the case of some of the experimental farms that we were working on, and also within the farming community over in Indonesia, we found variable stock size. So you would get some shrimp that would be stunted, some shrimp that would be at market size, but they were of the same age. So again, that's not very good for aquaculture. Very quickly talk about oysters. This is work that was done with Michael Dove, one of my former PhD students. Also had another 2 students working on this, one in particular, Alyssa Bishop. I'm not showing her work here, but I will talk about it briefly. So oysters in New South Wales and in other parts of the world are often grown in trays or on sticks, but a lot of the oyster farms in New South Wales and Queensland were experiencing unexplainable losses. So we embarked to look at whether acid played a role, and we did find that it did play a role. This is a photograph taken by Michael Dove, my ex-student, who's now the main oyster biologist for the New South Wales DPI. And you can see here the water isn't crystal clear. It isn't red with iron, but it does have aluminium sulfate coming through. And here the pH is not very low. It's low further up, but the aluminium sulfate, the flocks, are still potentially toxic. And they pass over these oyster leases. And these are some of the leases that were not producing the yields that they used to. And a lot of it had to do with land excavation, people draining the land for agricultural cropping purposes, livestock, etc., tea tree oil farming as well. And before that, they thought it was an unknown disease. This is a creek with a lot of iron in it. Very low pH water comes out of here. The thing with iron, when it oxidizes, even when the water becomes acidic again, it doesn't always redissolve, so it can hang around. And this is an oyster lease that was abandoned, and you can see iron all along the mud flat where that white arrow is. And that iron was smothering the oysters, and it was affecting their feeding. The acid that was coming in as well was also dissolving the oyster shell. So this is what ends up happening. If there are any oysters in a lease after heavy rainfall, the iron comes out and coats the oysters. That becomes a problem for marketing. The oysters can survive for about 3 weeks out of water, so farmers can pull them out for 3 weeks. But if the iron coats the oysters, it means they have to clean those oysters, which makes production more expensive for them. I have to talk very quickly because I think I'm going to be running out of time soon. Iron accumulation in the gills is a problem. We get that in fish, we get that in shrimp, and we get that in oysters as well. So here we've used a pearl Prussian blue type stain, and we've ended up showing where the lamellae have become clogged with the iron. So it shows up as blue. And these are oysters that were exposed to acid and not to a lot of iron, and it's actually bleached the shells. And what we found was the shell would perforate. It would perforate from the outside as a result of acid, and from the inside as a result of carbonic acid. The oysters would not feed, they would stay shut because they can sense and avoid the acidity. And as a result of that, they would accumulate acid, and that would eat away at the shell from the inside. So that's basically it in terms of impacts, but I'll just very quickly tell you that's all the bad news. Now, the good news is if you're in Indonesia, you have to talk to the Maros group because that group has been doing a lot of mapping. We also did a lot of experimental work, and we published all of that in the Indonesian Journal of Aquaculture on ways to remediate acid sulfate soils, ways to improve them. So although I've talked about what the issues and the problems are, there are solutions out there. The most important thing is to avoid these soils, and having really good site selection criteria and having good mapping protocols to identify them. So talk to Taruna Mulia, talk to Ahmad Mustafa, talk to the people at Maros, because they are the leaders in the area, in the region, on mapping these soils and coming up with strategies to try to get them to become more productive again. Thank you very much.
Thank you very much, Jess, for a really interesting presentation and great pictures too. So,
you're welcome. Sama-sama.
So I would like to, if the participant would like to ask some question, please go ahead. Please raise your hands using the Zoom systems, or just unmute and talk. It will be greatly appreciated. Yeah, go ahead, Pak Slamet Budi.
Yeah, thank you very much. Good afternoon, Jess. How are you?
Good, thank you. Good to see you.
Yeah, nice to see you. Jess, are there any technology to speed it up, to neutralize the pH on the acid soils in Tambak especially? Do you have any experience about that?
What we did at Maros when we were doing experimental work, we looked at lime. The problem with lime is that you need very large amounts of lime, and the lime needs to be integrated into the soil. When we did some work on the chemistry of soil dikes here in Australia, we found that a lot of the acidity is actually originating from deep inside the dike. So you get contributions from the surface of the dike, but also from deep inside the dike, where it's very difficult to get any lime into. So the farmers have a constant battle of having to continuously add lime to their system. When I was in India, one farmer added 70 tons of lime to his farm, which is an extraordinary amount of lime. So regular liming is important, but tidal flushing of the system, so basically washing the ponds with brackish water. Now, you have to think of the environmental impacts from that. So there is some work that we published on that. Ahmad Mustafa was the lead author on that work, so that's worth having a look at. So it really depends on the severity of the acidity. It's important to not to dry ponds out for too long, because if you dry them out for too long, you do get a lot of oxidation taking place. So in the dry season, that can be problematic. You may get oxidation occurring. Then in the wet season, the oxidation products will get washed into the system. It's best to avoid these soils in the first place. They are more expensive to manage. But tidal exchange is one of the ways. If you can do it in a way that you don't then overload the system, the off-site areas with a lot of iron, for example.
Okay. Are there any effect on the taste and then possibly on the texture of the fish or prawn if they live in the lower acid environment?
I'm not sure. We've never done any research on that, and I think that's an interesting thing to have a look at. I know the quality of fish and prawns are generally a little bit lower when they're grown in acid sulfate soils. There can be some texture changes, but I couldn't tell you with any confidence whether the taste. Although having said that, I have eaten mud lobsters that have grown in northern New South Wales aquaculture ponds, and they did have a metallic iron taste to them. So I think there is some absorption of the iron into the taste of the actual crab meat, but I couldn't be sure with prawns or fish.
Okay, thank you, Jess. I hope that answered your question, Pak Budi. We have Mirna Fitriani who would like to ask some question. She already raised her hand, so go ahead.
Thank you, Bang Hatim. My question is, I read some paper from Professor Jess talking about the same like before, like the participant before who asking the technology that can be overcome the acid sulfate soil problem. But the problem is when we use lime, we use in a massive amount. So even we combine with the teaching like Dr. Mustafa research, but the result is not going well as we expect. So is it okay if we combine with another technology that maybe you have experienced before, rather than bleaching or just liming, or we just avoid it? Because in Indonesia we have so many acid sulfur soil area that potential to be combined, to be explored to aquaculture. And the last question is, I saw the paper at the screen mentioned about geotide and jarosite. I thought first time it is similar, but is there any different? What the difference between geotide and jarosite? Thank you, Bang Hatim.
No worries.
You're welcome. Okay, so goethite is basically comprised of iron. So it's an oxidized iron. So it usually looks a little bit brown, orangey brown. It's a more advanced stage of oxidation than your normal iron oxide that looks like rust. So when you see goethite, the more orange colour, it means that the soil is oxidized for a long time ago. So that's a good indicator that that site was not recently disturbed. Jarosite's got a lot of potassium in it and a few other mineral compounds in it. So that's quite different. That's why you end up getting the yellow colour. There are different kinds of jarosite as well. You can look up the chemical formula. I can't rattle them off because it's a very long formula. So your jarosite is going to be present usually at weaker acidity, and your iron oxides will be more when the pH falls below 4. And the main reason is because of the acidity required to mobilise particular minerals. So you could actually have a look for jarosite in a clay soil, and you will see it follows very often the old root zones of mangroves. So it follows the areas where oxygen has moved in. Whereas in sandy soil, and you shouldn't be farming in sandy soils, but people do, but in sandy soils it will occur as like an efflorescence. It looks like a powder because air gets into sandy soil more easily. In terms of washing and leaching, again, it depends a lot on the soil type. So if you've got a very clayey soil, for example, the problem of iron coming from inside the dike is it's a slower problem. It takes a lot longer time for it to come out. The other issue too is to what extent has a clay soil cracked. Now we know aluminium flocculates clay, so it can create cracking, which can let oxygen in, but also can help to get acid out. So those sort of clays need to be very heavily limed. In more loamy, sandy soils, the depletion of pyrite is a lot faster because oxygen gets into those soils a lot quicker. It tends to accelerate oxidation. You can normally get lime products more easily into them, but usually those soils can be problematic because they don't hold water, so they will leak. So it is a question of how alkaline the tidal waters are, how much water can be funneled in and out of a system, what the canal network is like. So leaching and washing is not we call a silver bullet. It's not an answer for all of the conditions. So in some cases, you have to think, is it better to have aquaculture in these acid sulfate soils or look for an alternative farming practice? So so we've got avoid these soils as the number one issue. Where you already have farms, you have three things you can do. One is you can return the farm to a wetland, but most people don't want to do that because that's where their livelihood comes from. Secondly, they can invest in remediating the soil, but that can be problematic and you may not get excellent yields and the cost benefit might be very poor. Or you might look at an alternative land use. So looking at plant species, for example, that are acid and salt tolerant. Pineapples, for example, grow quite well in acid sulfate soil. There are other species that do. So, yeah, there is no single widespread ubiquitous solution to this particular soil type for people who are farming in these coastal lowlands. It is a challenge, and that's why I'm a I profess the importance of avoiding these soils in the first place. That they are very difficult to manage.
Okay.
Okay, thank you, Professor
You're
Jess.
welcome. Sama-sama.
Thank you, Bang Hatim.
Sama-sama. I think we already passed the time limit, Jess. So, I think for the question for your session, we have to start. And thank you so much for joining with us today. It was a great presentation and really great photos. I really love the lamella of Jill, so really great. So let's give some applause to Professor Jess Samuel for his contribution to this event. Thank you, Jess.
Thank you.
Excellent.
Okay, then, so I would like to give back the event to Pa Ilham, Pa Dr. Ilham, and so that he can close the event formally.
Yeah.
Please go ahead, Pa Ilham.
Thank you very much, my colleague Pa Hatim. We would like to again say thanks to all the audiences who keep staying with us until the end of the session. So again, on behalf of the steering joint committee of the Jakarta Technical University of Fisheries or Polytechnic AUP and Research Center for Fishery of the Ministry of Marine Affairs and Fisheries, we would like to express our big thanks and appreciation to all of the great speakers today from the US, from the Europe, and from Australia. And also, we would like to express our thanks to Professor Saribijaya for formally opening the session today. Also, we would like to appreciate the availability for and support from our director, Ibu Ani Lilani, the director for Jakarta Technical University of Fisheries, and all of the guests and participants today. We have noticed that they are coming from our range of institutions, from universities, from NGO, from schools, and even from private sectors and individuals. So hopefully what we have done today and all the knowledge and information can be very informative one, and I guess it was a very fruitful discussion today. So on behalf of the committee, I would like to close the session today. Greetings to you all, and then wishing all of us, success in the future. So I think that's all, Pa Hatim. Also here, I've seen quite few seniors and colleges, appear on the screen, like Pak Slamet Budi, thank you for joining us. Professor Ketut Sugama, thank you. Pak Taruna from South Sulawesi, and colleagues from, internally from Polytechnic AUP, my colleague Pak Bambang from LPL, and all other colleges. Sorry that I cannot mention one by one. So Pak Hatim, if you wish to add a few more.
I'd like to say thank you to Pak Taruna, and then first to the other speakers, thank you so much for spending time making the presentations. I really appreciate it. For Deba, Dr. Deba, Jess Samut, and Val, thank you so much. And also I would like to say hi to Pak Taruna Mulia, my college in Maros, and then my college in University of Halo Oleo. Some of you might not know the university, but that's where I came from.
Yeah,
so,
same like me. Same like me. I from Kendari, Sulawesi, from Konawe. Right. So very nice to meet all the colleges. Right.
Yeah. So just a quick a few announcement before Pak Ilham really close the meeting. Yeah, the event. So the material for the presentation will be provided in PDF files, but please be advised that some of the materials have not been published, especially for VAL presentations. So, and others, you can publish it or you can cite it, of course, using the regular academic citation standard. So please be aware of that so that we will have a really fair knowledge sharing between all of us as a researcher, academics, and practitioners. So I get back to you.
Yeah, thank you, my colleague Pak Hatim. So again, thank you, Prof. Mas Trijoko, my brother Alex from KKP, Pak Ervin. So I just mentioned like randomly what I've seen on my screen. So again, thank you very much. We wish to have another session with more interesting topic, of course. By saying Alhamdulillahirabbil alamin, I would like to formally close the session today. Wabillahi taufiq wal hidayah. Assalamualaikum warahmatullahi wabarakatuh.
Waalaikumsalam. Good afternoon.
Selalu Pak Ilham.
Ya, terima kasih Bu Evi di sini. And then I would like to acknowledge, thank you all the guys behind the scene from Polytechnic AUP. Bu Ika is the director of the International Partners Office. Bu Api, Pak Aulia, Mas Dika, for all of the support and fantastic technical assistance. Thank you.
Also for Research Center for Research Fisheries Research, Mbak Galuh, thank you so much for supporting this event. Bubut, Mas Heri, and then Mbak Gesti, thank you so much for your support. I hope that we can set another webinar with more preparation. So, but this is, I think, a great run for a first time webinar. So thank you so much.
Agree, Mbak Tia from BKIPM, yeah, thank you. Who else here? Yeah, many others, I guess, yeah. So, yes, my best wishes for you and all and other colleges in Sydney. Jess, very nice to meet you in Sydney last March. Yeah.
Same here.
So yeah. So thank you. Yeah.
You're welcome.
Very nice. Yeah. Bu Pigo, yeah, and para Prof. Rahmansa here.
Who
else? Yeah.
Here.
So, Pak Hatim, thank you very much for this collaboration. Also, on behalf of the Polytechnic AUP, we would like to appreciate your, collaboration, and hopefully this is not the first one. This is just the the stepping stone for another or for more collaboration. Thank you. I think I should close the online session today. Yeah. So in the next few minutes, so sorry that I have to finish off all the all of the connection. Thank you.
Thank you.
Thank you, Pailam. Thank you, Jess. Thank you, everybody, for listening today.
Goodbye, everyone. Well done.
Thank you. Have a great day today. Okay.
Mas Himawan, thank you, Mas Himawan.
Saya kira bisa kita switch ke bahasa Indonesia karena sudah tidak ada yang.
Oke, oh ya, terima kasih Bapak Ibu semuanya ya. Aduh, udah ini teman-teman di Polytechnic AUP ini, saya lihat tadi masih semangat semua, Pak Bongbongan, Bu Mira, Bu Sri, tadi ada Bu Amida, Bu Pigo, ini semuanya ya. Teman-teman dari luar juga, ini makasih banyak, Bu Gusti, itu masih ada juga. Iya. Sertifikat kita kirim via email ya, Pak Hatim Soleh, Pak Taruna, terima kasih. Pak Triheru, Bu Dewi, Pak Teguh.
Dan bahan-bahan bisa dicek di link yang sudah diberikan. Sekarang masih kosong karena ada proses proteksi. Mohon maaf sebelumnya. Nanti akan silakan dicek secara reguler di